Somewhere in the vast tapestry of the night sky, stretching quietly over our heads like a cosmic canvas, lies a silent giant. It doesn't shimmer or flash like the stars. It doesn't call attention to itself with flickers of motion or color. And yet, it is one of the most colossal structures visible from Earth, so massive and so ancient that it defies imagination. If you were to look up on a crisp, dark autumn night, far from city lights, you might see it as a faint smudge in the sky, subtle, soft, and ghostly. That smudge? That's no star. That's no cloud. That is the Andromeda Galaxy, our galactic neighbor, our cosmic cousin, and one day, perhaps, our future merger partner. But before we continue, subscribe to the channel and like the video. Let's take a journey across millions of light years and billions of years, to understand what makes this galaxy such a marvel in the eyes of astronomers, physicists, mythologists, and everyday stargazers alike. We'll explore its ancient mythological roots, its vast structure, the secrets of its stars, and the ultimate fate that binds it to our own Milky Way. But first, what exactly is the Andromeda Galaxy? The Andromeda Galaxy, known formally as Messier 31 or M31, is the nearest spiral galaxy to our own Milky Way and, perhaps more astonishingly, the largest galaxy in our local group, a collection of more than 50 galaxies including the Milky Way, the Triangulum Galaxy, M33, and numerous dwarf galaxies. Andromeda is an absolutely immense structure in space, stretching over 220,000 light-years in diameter and containing around 1 trillion stars. That's more than twice the number found in the Milky Way. Located approximately 2.5 million light-years away from Earth, Andromeda is the most distant object visible to the naked eye, a fact that alone is awe-inspiring. When you spot it in the sky, you're not just looking at something far away, you're peering 2.5 million years into the past. That smudge of light reaching your eyes tonight left its source before humans ever began to draw on cave walls. Astronomers have long been enchanted by Andromeda, not just because of its size and proximity, but because it offers a rare opportunity, a front-row seat to another spiral galaxy that we can study in depth. Most galaxies are far too distant to observe in such detail, but Andromeda provides a cosmic mirror of sorts. It's like standing on a mountaintop and seeing another mountain nearby that looks remarkably like your own. By studying Andromeda, scientists learn more about how spiral galaxies like ours form, evolve, interact, and eventually die. Andromeda is one of the brightest and best-studied galaxies in the sky. It's not just a topic of scholarly research, it's also a beloved object for amateur astronomers around the world. With even modest binoculars or a small telescope, you can start to make out the oval shape of the galaxy, and with better equipment, you can begin to see the dust lanes, star clusters, and satellite galaxies that orbit it. But this majestic object isn't just static. It's on the move, and it's coming straight for us. At a speed of roughly 110 kilometers per second, Andromeda is closing the gap between itself and the Milky Way, pulled by the mutual gravity of the two massive galaxies. While it will take around 4.5 billion years before they collide, astronomers have already mapped out the likely result, a titanic cosmic dance and merger that will reshape the local universe, forming a new supergalaxy often dubbed Milkomeda. The scale of Andromeda challenges the human mind. When we talk about distances in light-years and star counts in trillions, we're forced to stretch our imaginations. A single light-year is about 5.88 trillion miles. Multiply that by 2.5 million, and you begin to get a sense of just how vast the distance is, and yet Andromeda is still considered close by cosmic standards. It's not just the numbers that are fascinating. Andromeda plays a central role in the story of modern cosmology. The very fact that it's approaching us, blue-shifted rather than red-shifted like nearly every other galaxy, is an important piece in the puzzle of understanding the structure and motion of our universe. It breaks the general trend caused by the expansion of the universe, showing us how gravity still plays a dominant role on local scales. Moreover, when we look at Andromeda, we don't just see light. We see a living history of cosmic processes, galaxy mergers, star formation, supernovae, and the mysterious presence of dark matter. Scientists have used everything from optical telescopes to X-ray observatories and radio instruments to peel back the layers of this galactic neighbor. Andromeda is more than a glowing patch in the sky, it is a monument to time and space. A majestic swirl of stars, gas, and dust drifting through the universe. And just as Earth is not isolated in its solar system, and the solar system not isolated in the galaxy, the Milky Way is not alone in the cosmic ocean. Andromeda is a reminder that the universe is teeming with vast cities of stars, and that even on this enormous scale, we have neighbors. Let's turn our gaze from the grandeur of what Andromeda is, to the remarkable story of how it came to be known. Long before humanity understood what galaxies were, before we even understood that the stars were suns, or that the Earth orbited the sun, our ancestors still looked to the night sky with awe, wonder, and curiosity. Among the countless pinpricks of light, some objects stood out as odd. One such object was a faint, cloudy smear high in the autumn skies of the northern hemisphere, what we now know as the Andromeda Galaxy. This faint object was visible even to the unaided eye, assuming the observer had dark skies and sharp vision. Unlike the twinkling stars, this smudge had a diffused, almost ghost-like quality, as if the heavens had left a fingerprint on the sky. Ancient skywatchers, of course, had no idea what it was. They couldn't guess that they were looking at an entire galaxy, hundreds of thousands of light-years across, packed with hundreds of billions of stars. But they noticed it. They recorded it. And thus began Andromeda's long-documented presence in the history of human observation. The earliest known written reference to this object comes from the 10th century Persian astronomer Abd al-Rahman al-Sufi, one of the most brilliant minds of the Islamic Golden Age. In his famous astronomical treatise, The Book of Fixed Stars, 964 CE, al-Sufi described the object as a small cloud in the constellation of Andromeda. He called it a nebulous smear, and it was included in his catalogue of fixed stars, not because it was a star, but because it appeared unmoving in the sky. Al-Sufi's documentation was critical because it preserved a record of the object long before telescopes were invented. His text, which combined Greek astronomical knowledge with Arabic observations, served as a cornerstone for both Islamic and later European astronomy. When later astronomers began to systematically study the night sky with increasingly powerful telescopes, many turned to al-Sufi's writings as a guide, and so his record of this nebulous object lived on, connecting medieval skywatchers with today's cosmic explorers. Despite this early identification, Andromeda remained shrouded in mystery for centuries. In the absence of telescopic magnification, it was impossible to determine its nature. Was it a nearby cloud of gas within the Milky Way? A cluster of stars? An entirely separate universe? To understand just how little was known, we must consider the state of astronomy even up to the early 20th century. In the 18th century, Charles Messier, a French comet hunter, compiled a list of fuzzy objects in the sky so he wouldn't mistake them for comets. He catalogued these distractions to help comet hunters avoid confusion. And so, in 1764, the Andromeda Nebula was given the designation M31 in Messier's famous catalogue. This designation remains one of its primary names in astronomy to this day. Even as telescopes improved and the nebula was seen in more detail, with a central bulge and hints of spiral arms, its true nature was still debated. The brightest stars in the Andromeda Galaxy were just on the threshold of detectability with the technology of the time, making it difficult to measure its distance or determine if it lay within or outside the Milky Way. This brings us to one of the most pivotal figures in all of astronomy, Edwin Hubble. In the early 20th century, the scale of the universe was still unknown. Many astronomers believed the Milky Way was the entirety of the cosmos. The idea that other galaxies, island universes, as they were sometimes called, could exist beyond our own was a subject of fierce debate. This debate came to a head in 1920 in a public event known as the Great Debate, between two astronomers, Harlow Shapley, who argued that the Milky Way was the entire universe, and Heber Curtis, who believed in a universe populated with other galaxies. But it was Hubble who delivered the definitive answer. Using the 100-inch Hooker telescope on Mount Wilson in California, then the most powerful telescope in the world, Hubble began taking deep photographs of M31 in the 1920s. In these images, he discovered individual Cepheid variable stars, a type of pulsating star whose brightness changes in a predictable pattern. Thanks to the work of Henrietta Swan-Leavitt, who had earlier established the relationship between the brightness and period of Cepheid variables, Hubble was able to measure the distance to these stars. The result was staggering. The Cepheids in Andromeda were far too distant to be part of the Milky Way. They placed M31 at well over 900,000 light-years away, a number we now know is closer to 2.5 million, proving definitively that the Andromeda Nebula was not a gas cloud or a star cluster in our galaxy. It was an entirely separate galaxy, teeming with its own stars, its own structure, and possibly its own planetary systems. This single discovery changed the known scale of the universe overnight. Humanity's understanding of the cosmos expanded from one galaxy to many, and suddenly, the universe was no longer a single system. It was a vast collection of galaxies, each a cosmos of its own. Andromeda was the first galaxy proven to lie beyond the Milky Way. That realization was not just a breakthrough, it was a revolution. In honor of his role, the Hubble Space Telescope, launched decades later in 1990, bears Edwin Hubble's name, and it has gone on to capture some of the most breathtaking images of Andromeda ever taken, resolving thousands of individual stars and offering an unprecedented look at our neighboring galaxy in sharp detail. Let's return for a moment to the name itself, Andromeda. The galaxy takes its name from the constellation in which it appears, Andromeda, a figure from ancient Greek mythology. According to the myth, Andromeda was the daughter of King Cepheus and Queen Cassiopeia of Ethiopia. Her mother's vanity led her to boast that Andromeda was more beautiful than the Nereids, sea nymphs of Poseidon. As punishment, the god of the sea sent a sea monster, Cetus, to ravage their kingdom. To appease the gods, Andromeda was chained to a rock by the sea as a sacrifice. But just before Cetus could devour her, Perseus, returning from slaying the Gorgon Medusa, arrived on Pegasus and rescued her. This story was immortalized in the stars by ancient astronomers, who named the constellation Andromeda to honor her tale. Surrounding her in the sky are other mythological constellations: Cassiopeia the vain queen, Cepheus the king, Perseus the hero, Pegasus the winged horse, and even Cetus the sea monster. It's poetic that a galaxy of such cosmic significance should carry a name steeped in storytelling. After all, humanity has always wrapped the mysteries of the night sky in the fabric of myth. To our ancient ancestors, the heavens were not just distant lights. They were stories, gods, warnings, and heroes written across the blackness. The Andromeda Galaxy carries that legacy forward, a modern wonder with ancient roots. And so, from a vague smudge in the sky noted by medieval astronomers, to a pivotal proof of the vastness of the universe by Hubble, and bearing a name born of ancient myth, the Andromeda Galaxy has journeyed with humanity through time. Its discovery is not the story of a single moment, but of a long chain of observation, curiosity, and revelation, one that continues to this day as we explore its depths with new technologies and deeper questions. To find the Andromeda Galaxy in the vast sea of stars, you don't need a telescope or even binoculars, just a clear, dark night, a bit of patience, and some orientation in the sky. The experience of locating it is an act of cosmic humility. Standing on a tiny rock orbiting an average star, looking out across 2.5 million light-years to behold a galaxy far grander than our own, visible with just your eyes. So how do you find this majestic neighbor? Andromeda is nestled in the constellation of the same name, Andromeda, named after the mythical princess chained to a rock. This constellation lies in the northern hemisphere's autumn sky, making September through November the ideal time to view the galaxy. During these months, Andromeda climbs high into the evening sky, positioned almost overhead by late night, especially for observers in mid to high northern latitudes. The best part? You don't need fancy equipment. Under a truly dark sky, far from city lights, the Andromeda Galaxy appears as a faint, elongated smudge, about the size of the full moon, though far dimmer. Let's break down how to find it step by step. Step 1. Locate the Great Square of Pegasus. Start by finding the Great Square of Pegasus, a prominent asterism made up of 4 bright stars forming a large, nearly perfect square. This shape is relatively easy to identify in the eastern evening sky during autumn. It forms part of the Pegasus constellation, which represents the mythological winged horse. From the top left corner of the square, the star called Alpheratz, which is technically shared by both Pegasus and Andromeda, you can trace your way toward the Andromeda constellation. Step 2. Follow the line of stars into Andromeda. From Alpheratz, look for 2 curved lines of stars extending to the northeast. These form the body of Princess Andromeda in the sky. The lines contain stars that appear almost like a long, bent arm stretching away from the Pegasus square. Follow the top row of these stars for 2 or 3 stars. This line points you toward the approximate region where the Andromeda Galaxy resides. Step 3. Identify Merope and Mu Andromedae. Look for the star Merope, a second-magnitude orange-hued star located along that curved line. From Merope, move upward, northward, to a dimmer star named Mu Andromedae. Now, here's the trick. From Mu, move the same distance and direction again. That's where the Andromeda Galaxy is located. If your eyes are dark adapted, and you're in a place without light pollution, you'll see a dim oval glow. That faint light you're perceiving has traveled millions of years to reach you, emitted by billions of stars in a galaxy far beyond our own. When and where to look? A best time, late summer to early winter, is prime viewing time, particularly September through November. In August, Andromeda rises later in the night, but by October, it's already well placed in the sky by early evening. A best conditions. To see Andromeda with the naked eye, you'll need dark sky conditions, far from city lights, with little moonlight and low humidity. A new moon night in a rural area offers the best chance. A latitude range. Andromeda is visible from almost all of the northern hemisphere, and even from some southern latitudes near the equator. The farther north you are, the higher it rises in the sky, which improves visibility. A position in the sky. Andromeda is a circumpolar constellation for far northern latitudes, meaning it never sets below the horizon. But for most observers, it rises in the northeast and arcs high across the sky by midnight in autumn. What you'll see. With the naked eye, Andromeda appears as a faint, elongated smudge, a ghostly presence that contrasts with the pinpoint sharpness of stars. The brighter central core is what you'll most likely notice first. Under excellent sky conditions, the galaxy can appear over 3 degrees wide, about 6 times the width of the full moon. With binoculars, the view is even better. The central bulge appears brighter and more detailed, and the galaxy's extended spiral shape becomes more pronounced. You may even start to detect hints of dust lanes and the presence of Andromeda's companion galaxies, M32 and M110, as small fuzzy patches nearby. With a telescope, especially one with a wide field of view, the galaxy truly comes to life. You'll see the core glowing brightly and the faint spiral arms stretching outward. However, because Andromeda is so large in angular size, smaller telescopes or wide-field views often provide more satisfying images than high magnification. The most distant object you'll ever see. With just your eyes. Here's a fact that should stop you in your tracks. The Andromeda Galaxy is the most distant object visible to the naked eye. At 2.5 million light-years away, the photons reaching your retina tonight began their journey long before human civilization existed. Dinosaurs were long extinct. The very earliest ancestors of humans had not yet walked upright. The light you see now has traveled across intergalactic space, unimpeded, for millions of years, only to end its voyage in your eye. It's a moment of direct connection across the cosmos, a bridge between your own brief life and the vast, ancient structure of the universe. To put it into perspective, when you look at Andromeda, you're seeing it as it was 2.5 million years ago. You're not observing its present state. If a civilization existed there and was observing us in return, they would see Earth in its prehistoric state, without cities, satellites, or even humans. This is one of the most profound truths about stargazing. We don't just see space, we see time. The farther we look, the deeper we peer into the history of the universe. And Andromeda offers a rare opportunity to touch that ancient light with your own eyes. Why this matters for amateur astronomers. Andromeda is often one of the first deep sky objects that amateur astronomers seek out. It's relatively easy to find once you're familiar with the night sky, and it's rewarding to observe across all levels of equipment, from the naked eye to binoculars to sophisticated telescopes. Even if you're new to astronomy, hunting for Andromeda teaches you the art of star hopping, enhances your awareness of light pollution, and tunes your eyes to detect subtle contrast. These skills open the door to the broader world of deep sky observing. It's also a powerful gateway to curiosity. Observing Andromeda raises questions naturally. What are those companion galaxies next to it? How far away is it really? Are there planets in that galaxy? Could there be life there? What will happen when it collides with our galaxy? Each question draws you deeper into the cosmic mystery, and each answer unfolds new layers of understanding. And so, high above our heads on clear autumn nights, the Andromeda Galaxy drifts silently. It has been there for billions of years, unchanging to the naked eye, quietly reminding us of our place in a vast, interconnected universe. And with nothing more than your own 2 eyes and a sense of wonder, you can find it, connect with it, and be part of a lineage of skywatchers stretching from ancient Persia to modern astrophysics. Now that we know how to find the Andromeda Galaxy in the night sky, and have grasped the sheer awe of seeing it with our own eyes, it's time to dig into the cold, hard facts. Because while the mythology and visual beauty are compelling, it's the numbers and measurements that truly illustrate just how monumental Andromeda is. This is where science meets scale, numbers so vast they border on the poetic. Let's dive into the vital statistics of our galactic neighbor and start to build a complete understanding of what makes Andromeda such a cornerstone of modern astronomy. Distance: 2.537 million light-years away. First and foremost, Andromeda is located approximately 2.537 million light-years from Earth. That means the light we see when we look at it tonight left the galaxy 2.5 million years ago, when early human ancestors like Australopithecus afarensis roamed the plains of Africa. But let's put that number into perspective. A 1 light-year equals about 5.88 trillion miles, 9.46 trillion kilometers. So 2.537 million light-years equals approximately 14.9 quintillion miles, or 24 quintillion kilometers. That number is so large that it becomes meaningless without comparison. If the Sun were the size of a small pea, Earth would be a grain of sand about a meter away. On that same scale, the Andromeda Galaxy would be another collection of sand grains roughly 4,000 kilometers away, about the distance from London to New Delhi. Even within the vastness of the universe, Andromeda is considered close. In fact, it's part of our local group, a small cluster of about 54 known galaxies bound together by gravity. Among these galaxies, Andromeda is not just nearby, it's also the largest. Size: over 220,000 light-years in diameter. Andromeda spans a staggering 220,000 light-years across from one end of its spiral disk to the other. To grasp this, consider that our own Milky Way galaxy is around 100,000 to 120,000 light-years in diameter, depending on how you define the edge. This means Andromeda is nearly twice as wide as the Milky Way. In more concrete terms, if light could travel in a straight line through Andromeda's diameter, it would still take more than 2 centuries to cross it. And remember, light travels at 299,792 kilometers per second. That's fast enough to go around the Earth 7.5 times in 1 second. Andromeda's sheer size gives it a gravitational footprint large enough to dominate the local group. It exerts a significant influence on neighboring dwarf galaxies, as well as on our Milky Way. The outer reaches of its halo, a diffuse, spherical cloud of old stars and dark matter, may even extend halfway to the Milky Way itself, and our galaxy's halo likely does the same. Stellar population: 1 trillion stars. One of the most jaw-dropping statistics about Andromeda is its estimated star count, approximately 1 trillion stars. Compare that with the Milky Way, which is thought to contain 100 to 400 billion stars, and it becomes clear why Andromeda has long been considered the largest galaxy in our neighborhood, not just in physical size but also in stellar population. Among these trillion stars are a wide range of types. Massive blue stars, burning brightly but living short lives. Long-lived red dwarfs, the most numerous type of star in the universe. Red giants and white dwarfs, remnants of older generations. Entire globular clusters, each containing hundreds of thousands of tightly packed stars. These stars are spread across Andromeda's central bulge, spiral arms, disk, and halo, forming structures that reflect billions of years of cosmic evolution. Mass and gravity: over 1.5 trillion solar masses, including dark matter. In terms of total mass, including both visible matter and dark matter, Andromeda is estimated to weigh between 1.5 to 2 trillion times the mass of our Sun. Much of this mass is not in stars or gas, but in dark matter, the mysterious substance that neither emits nor absorbs light but exerts gravitational force. Dark matter forms an invisible halo around galaxies, extending far beyond their visible edges. In Andromeda, as in the Milky Way, this halo is thought to be 10 times more massive than the visible galaxy itself. The immense gravitational pull of this mass is what allows Andromeda to anchor multiple satellite galaxies and is also why it is on a collision course with the Milky Way. More on that in a future segment. Rotation and movement. Rotates once every 220 million years. The entire Andromeda Galaxy rotates, a rotation so vast it takes roughly 220 million Earth years to complete a single turn. That's the same as our own Milky Way's rotation period, despite Andromeda being larger. The outer regions of the galaxy move at hundreds of kilometers per second. But perhaps more astonishing is Andromeda's motion through space. Unlike most galaxies, which are moving away from us due to the universe's expansion, causing a redshift, Andromeda is moving toward us, creating a blue shift in its light. It is approaching at a speed of 110 kilometers per second, that's 396,000 kilometers per hour, or roughly 246,000 miles per hour. Fast enough to circle the Earth in 10 minutes. Catalog names and designations. While Andromeda Galaxy is its most popular name, astronomers often refer to this galaxy by its catalog designation, M31. The M stands for Charles Messier, the French astronomer who compiled a list of celestial objects that could be confused with comets. The Andromeda Galaxy is number 31 on that list, hence M31. Other designations include NGC 224, in the new General Catalogue of Nebulae and Clusters of Stars, a UGC 454, in the Uppsala General Catalogue, a PGC 2557, in the Principal Galaxies Catalogue. But for both professionals and enthusiasts, M31 remains the most frequently used shorthand. Brightness, apparent magnitude of 3.4. Andromeda's brightness makes it a rare treat for observers. It has an apparent magnitude of 3.4, which makes it visible to the naked eye under dark skies, easily visible through binoculars, a rewarding target for small telescopes. The magnitude scale is logarithmic, so every increase of 1 represents a 2.5 times difference in brightness. For context, the faintest stars visible under ideal naked eye conditions are about magnitude 6. So at magnitude 3.4, Andromeda is faint but still well within visual reach for most observers. Keep in mind, though, its light is spread over a wide area, so it doesn't appear as bright as a star of the same magnitude. But once you know where to look, and especially when using binoculars, it becomes an unmistakable presence in the night sky. Shape and orientation. Andromeda is a barred spiral galaxy, like the Milky Way, although we often refer to it simply as a spiral galaxy. It appears at an inclined angle from our point of view, about 77 degrees, so we don't see it face-on or edge-on, but at a diagonal slant that reveals its elliptical shape in the sky. This orientation allows us to study many of its features in good detail. Its spiral arms, dust lanes, and satellite galaxies all stand out more clearly than they would in a face-on view. So when you stand beneath a dark, star-filled sky and look toward the constellation Andromeda, you're not just gazing at a beautiful patch of light, you're seeing a massive spiral galaxy, 2.5 million light-years away, a home to 1 trillion stars, a 220,000 light-years across, a hurtling toward us at 110 kilometers per second, surrounded by dozens of smaller galaxies, and bright enough to be seen without a telescope. In every way that matters, size, scale, age, motion, Andromeda is a galactic titan. And yet, it's close enough for us to study in remarkable detail, making it one of the most significant astronomical objects in the night sky. It's not just a neighboring galaxy, it's a cosmic milestone, a reference point, a key to unlocking the structure and fate of the universe. When we look at the Andromeda Galaxy with the naked eye or even through a pair of binoculars, what we see is a faint, fuzzy patch, a gentle smear of light in the night sky. But behind that modest glow lies a galactic masterpiece of architecture and physics. Andromeda is a barred spiral galaxy, and like all spiral galaxies, its structure is defined by motion, gravity, gas, stars, and time, all woven together into a dynamic system that spans hundreds of thousands of light-years. To understand Andromeda's structure is to peek under the hood of one of the grandest engines in the universe. Let's break it down, component by component, and explore how this galaxy is built from the inside out. The barred spiral shape. The Andromeda Galaxy belongs to a classification of galaxies known as SBB-type galaxies in the Hubble sequence, a subset of barred spiral galaxies. This means that, at its core, it doesn't just contain a simple spherical bulge like many spirals. Instead, it has a bar-shaped structure of stars that extends through the center and connects to the spiral arms. These bars are made of older, cooler stars and are believed to play an important role in the dynamics of the galaxy, specifically in channeling gas and dust toward the core, fueling star formation and even feeding the supermassive black hole at the center. Barred spiral galaxies are quite common in the universe. Our own Milky Way is one, and the presence of a bar may represent a later stage in galactic evolution. It suggests that Andromeda, like the Milky Way, has undergone complex internal changes over billions of years. Central bulge, the galactic core. At the heart of Andromeda lies its central bulge, a densely packed region of stars, gas, and dust that forms the nucleus of the galaxy. This bulge is oval in shape and consists primarily of older, redder stars, many of which are low mass and long-lived. This hints at the ancient history of the core. Some of the stars here could be over 10 billion years old, remnants from the early days of Andromeda's formation. The central bulge of Andromeda is not only larger than that of the Milky Way, but also more luminous, owing in part to its more massive stellar population. Within this bulge lies a supermassive black hole, which we'll explore in more detail in a later segment. For now, just know that the gravity well at the center of Andromeda is millions of times more massive than our Sun, anchoring the orbits of stars and gas in the inner galaxy. This region is also rich in metallic elements. Astronomers refer to any element heavier than hydrogen and helium as metals, indicating that many generations of stars have lived and died here, enriching the surrounding environment with the byproducts of supernovae and stellar winds. Spiral arms, star-forming engines. Extending outward from the central bulge are Andromeda's iconic spiral arms, vast curving streams of stars, gas, and dust that wrap around the galactic core in a graceful, yet tightly wound, configuration. Unlike the arms of more loosely structured spiral galaxies, Andromeda's arms are relatively compact and well-defined, giving it a classic pinwheel shape when viewed in full. These spiral arms are not static structures. They are shaped by density waves, regions of higher gravitational influence that compress gas and trigger star formation as they sweep through the galactic disk. As gas clouds enter these waves, they collapse and form young, hot, blue stars, many of which live short, brilliant lives and end in dramatic supernovae. In high-resolution images, especially those taken by the Hubble Space Telescope or ground-based observatories using adaptive optics, we can see dark dust lanes threading through the arms, outlining the structure like the cracks in an old painting. These dust lanes are cool, dense regions where future generations of stars may eventually form. The spiral arms are not uniform. There are regions where star clusters, nebulae, and stellar nurseries gather in higher concentrations. These features give us clues about the star formation rate, the age distribution of stellar populations, and the dynamics of interstellar matter within the galaxy. Galactic disk, the broad canvas. The spiral arms are embedded in the galactic disk, a vast, flattened plane of stars, gas, and dust that defines the visible shape of the galaxy. Andromeda's disk is extensive, stretching across more than 220,000 light-years, and is inclined at about 77 degrees to our line of sight, meaning we see it almost edge-on, but not quite. This gives us a beautifully elliptical appearance that reveals both the structure of the arms and the depth of the core. The disk contains most of the galaxy's younger stars, as well as massive molecular clouds where star formation is ongoing. It also harbors a variety of stellar populations, including open clusters, or loosely bound groups of young stars. Arobi associations, large groups of massive, hot, short-lived stars. Nebulae, both emission and reflection types. Supernova remnants, the aftermath of massive stellar explosions. Over time, the disk has evolved through mergers with smaller galaxies, internal dynamics, and the influence of dark matter, leading to distortions, warps, and rings that astronomers continue to study in detail. Galactic halo, the ancient sphere. Surrounding the disk is the galactic halo, a roughly spherical region that extends far beyond the visible limits of the galaxy. The halo contains very old stars, often in globular clusters. A dark matter, which dominates the galaxy's total mass. Tidal streams, remnants of past galaxy mergers. The halo is diffuse and faint, but it holds some of the most ancient stellar populations in the galaxy. These stars are typically metal-poor, meaning they contain fewer elements heavier than helium, suggesting they were formed in the early universe. The halo also contains stellar streams, long, thread-like structures of stars that were torn from smaller satellite galaxies during past mergers. These streams are like forensic evidence, allowing astronomers to reconstruct Andromeda's violent past and better understand how large galaxies grow by accreting smaller ones. And then there's the dark matter halo, the invisible skeleton of Andromeda. Although we can't see it directly, We infer its presence from the galaxy's rotation curve, the way stars and gas orbit the center. Instead of dropping off at the edges as Newtonian physics would predict, the orbital speeds remain nearly constant far into the outskirts of the galaxy. This implies there is far more mass than what we can account for with visible matter. In fact, the dark matter halo likely extends several 100,000 light-years from the center, making it the dominant component of Andromeda's gravitational field. Visualizing Andromeda, a galactic city. Imagine Andromeda as a vast cosmic city. At the core is like the city center, bright, dense, old, and bustling with history. At the bar is a highway cutting through the downtown, channeling resources to the heart. At the spiral arms are the neighborhoods, full of life, birth, and activity. At the disk is the greater metropolitan area, extending far and wide, diverse and dynamic. At the halo is the quiet countryside, less crowded, older, and home to the elders and monuments of the galaxy's past. And then, surrounding the entire city, like a ghostly force field, is the dark matter halo, silent, invisible, but deeply influential. Using visuals and animations. 4 video presentations, especially on YouTube, visualizing Andromeda's structure is essential. Here's how you could bring it to life. 1. 3D animations. Fly through Andromeda, starting at the outer halo, diving into the spiral arms, circling the core, and zooming back out. 2. Layered cutaways. Show a diagram peeling away the galaxy's layers, from the disk to the core to the halo. 3. Comparative overlays. Superimpose the Milky Way over Andromeda to show size and structure differences. 4. Time-lapse simulations. Use cosmological models to animate how the spiral arms rotate, how stars move within the disk, and how gas flows toward the center via the bar. These visuals don't just inform, they immerse the viewer in the galactic experience, making the abstract concrete and the immense graspable. Andromeda is not a static painting in the sky, it is a living, breathing galactic ecosystem. It rotates, it evolves, it gives birth to new stars, and it bears the scars of ancient collisions. Its structure, bar, bulge, arms, disk, halo, is a monument to gravity's relentless artistry over billions of years. And by understanding how it's built, we learn not just about this single galaxy, but about the very mechanisms that shape galaxies across the universe. When we talk about the Andromeda Galaxy, it's natural to ask, how does it compare to our own Milky Way? After all, both galaxies are spiral giants, the 2 largest members of our local group, and, fascinatingly, they are on a cosmic collision course with one another. Understanding the relationship between these 2 galaxies is like comparing 2 massive, ancient cities, each with its own neighborhoods, history, and architecture, yet destined to eventually become one. So, let's explore this galactic sibling rivalry, Andromeda versus the Milky Way. Size. Andromeda is slightly larger. Let's begin with size, perhaps the most obvious metric for comparison. Andromeda's diameter, 220,000 light-years. A Milky Way's diameter, 100,000 to 120,000 light-years. Some estimates extend up to 200,000 light-years when including the extreme outer disk and halo. This means that Andromeda is at least 1.5 to 2 times wider than the Milky Way, depending on how we define the edge of each galaxy. It's worth noting that defining the edge of a galaxy is tricky. It's not like a city wall, but more like a gradual fading of stars and gas into space. Recent observations suggest that the Milky Way may have more extended gas and dark matter than we once believed, but Andromeda still wins in terms of total visible width. So, in pure physical dimensions, Andromeda is our big brother in the local group. Stellar population. Andromeda has more stars. When we count stars, the difference becomes even clearer. Are Andromeda's stars, estimated 1 trillion. A Milky Way stars, estimated 200-400 billion. That's more than double, possibly even 5 times the number of stars in our own galaxy. This gives Andromeda a significantly greater stellar mass, though the actual total mass of each galaxy, when including dark matter, may be more evenly matched. Interestingly, although Andromeda has more stars, the Milky Way may actually be more massive overall, depending on which estimates you trust. Some studies based on star velocities and satellite motion suggest that the Milky Way's dark matter halo could be heavier than Andromeda's, as much as 1.6 trillion solar masses versus Andromeda's 1.5 trillion, although these numbers are still being refined with better data from missions like Gaia. So the story isn't entirely simple. Andromeda has more stars and larger diameter, but the Milky Way may have more dark matter, making it possibly the more massive of the two, despite appearances. Structure: spiral galaxies with bars. Both Andromeda and the Milky Way are barred spiral galaxies, which means they share a similar basic structure. A central bulge filled with old stars. A bar structure of stars and gas crossing the core. Spiral arms extending outward in a rotating disk. A surrounding halo populated with ancient stars and globular clusters. An extended dark matter halo that outweighs all visible matter. Their spiral arms are home to star-forming regions, molecular clouds, and young, hot stars. The bars are thought to help funnel gas into the central regions of the galaxies, possibly feeding the supermassive black holes at their cores and influencing star formation. However, there are some structural differences worth noting. Andromeda's arms are relatively tightly wound and more clearly defined, while the Milky Way's arms are more loosely wrapped and may include several major arms like Perseus, Sagittarius, and Scutum Centaurus. Andromeda's disk appears less warped than the Milky Way's, which may be a sign of fewer recent interactions or different satellite dynamics. Andromeda's bulge is more elliptical and brighter than ours, suggesting a different star formation history in the core. Meanwhile, the Milky Way shows more signs of ongoing star formation in the disk, and its bar may be more prominent or active. Satellites. Each has its own galactic family. Both galaxies are not alone. They are each surrounded by swarms of smaller satellite galaxies that orbit like moons around planets. These dwarf galaxies range from faint star clusters to complex systems of their own. Andromeda has at least 35 confirmed satellites, including M32 and M110, which we'll explore in the next segment. Some of these satellites show signs of interaction and merging, feeding Andromeda with new stars and mass. The Milky Way has around 50+ known satellites, including the large and small Magellanic Clouds, which are bright enough to be seen with the naked eye from the southern hemisphere. Interestingly, studies suggest that some of these satellites may orbit in coherent planes or move in synchronized patterns, a mystery that challenges some current models of galaxy formation. These satellite galaxies are important clues in understanding galactic evolution. Both Andromeda and the Milky Way have absorbed or are currently tidally stripping some of their satellites, leaving behind stellar streams in their halos. These streams act like cosmic fossils, showing where past mergers occurred and revealing the complex dance of gravity over billions of years. Star formation rate. Currently, the Milky Way has a higher star formation rate than Andromeda. A Milky Way, 13 solar masses worth of new stars per year. Andromeda, 0.5 solar masses per year. This means the Milky Way is, for now, a more active stellar nursery, while Andromeda appears to be in a more quiescent phase, though it still forms stars in its spiral arms. However, both galaxies have gone through periods of high activity in the past, often triggered by galactic interactions, such as the ingestion of dwarf galaxies or the influence of passing satellite systems. Supermassive black holes. Each galaxy has a supermassive black hole at its center. A Milky Way's black hole, Sagittarius A*, 4.3 million solar masses. Andromeda's central black hole, 200 million solar masses. Yes, you read that right. Andromeda's central black hole is 25 to 50 times more massive than the Milky Way's. Despite this, it is not currently very active, meaning it does not emit significant radiation or jets. It lies mostly dormant, likely because there is not much matter currently feeding into it. The Milky Way's black hole, Sagittarius A*, is also quiet but has flared occasionally in the past, possibly due to small stars or gas clouds passing too close. Dominant galaxies of the local group. Together, the Milky Way and Andromeda are the titans of the local group, a gravitationally bound cluster of galaxies that includes the Triangulum Galaxy, M33, a few dozen dwarf galaxies, and numerous faint satellites. Andromeda and the Milky Way make up about 90% of the total mass of the local group. At the center of mass of the local group lies roughly between the two galaxies. Over time, both galaxies influence each other gravitationally, causing tidal effects and slowly drawing closer together. Their sheer size, mass, and influence mean that they shape the evolution of all other members of the local group. Their interactions, including the eventual merger, will determine the future of our galactic neighborhood. Cosmic twins, but not identical. So, to summarize the key comparisons. Property Andromeda, M31, Milky Way. Diameter tilde 220,000 light-years tilde 100,000,120,000 light-years. Star count tilde 1 trillion tilde 200,400 billion. Mass, total, tilde 1.5 trillion solar masses tilde 1.6 trillion solar masses, estimated. Spiral type barred spiral, SBB, barred spiral, SBC. Star formation rate tilde 0.5 solar masses, year tilde 13 solar masses year. Satellites tilde 35 plus tilde 50 plus. Supermassive black hole tilde 100-200 million solar masses tilde 4.3 million solar masses. While both galaxies share many structural similarities, they also have their own unique traits, histories, and evolutionary paths. They are siblings, yes, but more like fraternal twins than identical ones. Each has helped shape its corner of the universe, and together, they represent two of the most important laboratories for understanding galactic formation and evolution in the cosmos. Soon, they won't just be neighbors, they'll be one galaxy, but we'll save that story for a later chapter. Now that we've compared the majestic Andromeda Galaxy with our own Milky Way, it's time to shift our focus outward slightly, to the company Andromeda keeps. Because just like our galaxy has the large and small Magellanic Clouds, Andromeda is surrounded by a bustling neighborhood of smaller, dimmer satellite galaxies that orbit it in intricate, gravitationally bound relationships. Among these, M32 and M110 are the two most prominent and scientifically significant. But they're far from alone. Andromeda commands a swarm of more than 30 confirmed satellite galaxies, and possibly many more that remain undiscovered. Let's delve deep into the world of Andromeda's satellite galaxies, starting with its brightest and best-known companions. M32, the bright, compact neighbor. Officially known as Messier 32, or NGC 221, this little elliptical galaxy punches well above its weight when it comes to cosmic influence. Discovered by Guillaume Le Gentil in 1749 and later catalogued by Charles Messier, M32 sits just below the disk of Andromeda when observed from Earth. It's relatively easy to spot with a decent telescope or in long-exposure astrophotography, appearing as a compact, fuzzy ball of light near Andromeda's central bulge. Key characteristics of M32. A galaxy type, compact elliptical, CE2. A distance from Earth, tilde 2.5 million light-years, roughly the same as Andromeda. A apparent magnitude, tilde 8.1. A size, tilde 6,500 light-years across. A stellar population, primarily older stars with little active star formation. What makes M32 unique is its extremely high surface brightness and compactness. It's packed with stars in a relatively small volume, which gives it a very dense, tightly bound structure. The core of M32 contains a supermassive black hole estimated at around 2 to 3 million solar masses, further anchoring the galaxy's dense interior. But M32 is more than just a dense ball of stars. It's possibly the remnant of a once larger galaxy that had its outer layers stripped away by tidal forces from Andromeda. Galactic cannibalism? There's growing evidence that Andromeda may have consumed much of M32's outer disk in the past, leaving behind the compact core we now see. In this scenario, M32 would be the exposed heart of a once much larger spiral or elliptical galaxy. This idea is supported by signs of tidal interactions, including star streams and the unusually high stellar density of M32's nucleus. This speaks to a broader theme: galaxies grow by devouring others, and M32 may be both a witness and a victim of Andromeda's galactic appetite. M110, the asymmetrical understudy. Now we turn our eyes to Messier 110, or NGC 205. M110 is slightly larger and more diffuse than M32 and appears on the opposite side of Andromeda's disk from our vantage point on Earth. Key characteristics of M110. A galaxy type, dwarf elliptical, D5. A distance from Earth, tilde 2.69 million light-years. A apparent magnitude, tilde 8.9. A size, tilde 17,000 light-years across. A stellar population, mostly old stars, but with evidence of recent star formation. Unlike the compact and intense M32, M110 is more extended, with a noticeable elongation and asymmetrical structure. Its outer regions show dust lanes, a rare feature in elliptical galaxies, which suggests it has retained some gas and dust, a sign that star formation may have occurred relatively recently, at least on a cosmic timescale. In fact, M110 may have undergone a burst of star formation within the last few billion years, possibly triggered by gravitational interactions with Andromeda. Some researchers even suggest that tidal forces from Andromeda may be actively distorting M110's shape, pulling it into an elongated arc and stirring up star-forming activity. It's a classic case of a small galaxy being buffeted by the gravitational tides of its larger neighbor. M110, like M32, also lacks a significant central black hole, though its stellar content and complex internal dynamics continue to puzzle and fascinate astronomers. The gravitational dance. Both M32 and M110 are gravitationally bound to Andromeda, meaning that they orbit it much like moons orbit a planet, albeit on much longer, elliptical trajectories that may take billions of years to complete. These satellite galaxies are not just passive companions, they are active participants in Andromeda's evolution. Their close encounters, tidal forces, and even mergers influence the morphology, star formation rate, and stellar dynamics of Andromeda's disk and halo. Andromeda's halo, in particular, is littered with tidal streams, diffuse trails of stars that were once part of smaller galaxies like M32, M110, or others long ago absorbed or disrupted by the larger galaxy. These stellar streams are like fingerprints, tracing the violent history of galactic cannibalism that helped Andromeda grow into the giant we see today. Other notable satellites of Andromeda. Beyond M32 and M110, Andromeda hosts an extended family of dwarf spheroidal and irregular galaxies. Some notable members include NGC 147 and NGC 185. These are dwarf spheroidal galaxies, both located near M31 and showing signs of recent star formation. They are among the more massive Andromeda satellites after M32 and M110. Are Andromeda I through Andromeda XXVII, and counting. These are a series of faint dwarf spheroidal galaxies named sequentially as they were discovered. Many of them are extremely low in brightness, dominated by dark matter, and exhibit no star formation, yet they are critically important for studying the dynamics of the local group and the nature of dark matter. A triangulum galaxy, M33, while often considered a member of the local group in its own right, M33 is sometimes thought to be gravitationally linked to Andromeda, possibly in a very wide, distant orbit. We'll talk more about M33 in a later section. Impacts on Andromeda's structure. So how exactly do these satellites shape Andromeda itself? 1. Disk warping and heating. Gravitational tugs from passing satellites, especially during close encounters, can warp the disk of a galaxy, disturb its spiral arms, and create ripples or flares in the stellar population. Andromeda's outer disk appears warped, possibly due to such interactions. 2. Triggered star formation. The gravitational compression caused by a satellite's close passage can trigger bursts of star formation in localized regions, as gas clouds are compressed into stars. Some star-forming regions in Andromeda's spiral arms may owe their existence to such events. 3. Mass accretion. When a satellite galaxy is fully absorbed, Andromeda gains new stars, gas, and dark matter, adding to its overall mass and potentially reshaping its halo. 4. Galactic archaeology. Tidal debris from these satellites leaves behind star streams and substructures in Andromeda's halo. Studying these remnants allows astronomers to reconstruct past events, like cosmic detectives piecing together the history of past mergers. The bigger picture, satellite systems in the local group. Studying Andromeda's satellite galaxies doesn't just tell us about Andromeda, it also helps us understand the hierarchical formation of galaxies throughout the universe. According to the lambda-cold dark matter (CDM) model, galaxies grow by merging with smaller ones, and satellite systems like M32 and M110 are living proof of this process in action. They also provide a valuable testing ground for theories about a dark matter distribution in dwarf galaxies, a tidal stripping and mass loss, a star formation suppression in small halos, and the evolution of galactic disks and halos. In other words, these little galaxies are more than just hangers-on, they are critical pieces of the cosmic puzzle. And as we gaze up at the night sky and see the fuzzy glow of Andromeda, we're not just looking at a single galaxy, we're seeing a cosmic metropolis, surrounded by dozens of satellite suburbs, all dancing to the gravitational rhythm of one of the universe's great giants. Now that we've explored Andromeda's intricate network of satellite galaxies and the gravitational web that binds them, let's shift our focus inward, to the very building blocks of the galaxy itself, its stars. The Andromeda Galaxy, or M31, is home to one of the richest and most diverse stellar populations in the known universe. From ancient red giants in its vast halo to the brilliant, young blue stars that blaze along its spiral arms, Andromeda offers a cross-section of stellar life and galactic evolution that's both fascinating and illuminating. Understanding the star composition within Andromeda isn't just about counting stars or labeling their colors. It's about tracing the deep cosmic history of how this galaxy came to be, how it has evolved, and where it might be going. Stellar populations, the two major classes. To make sense of Andromeda's stellar makeup, astronomers often refer to two broad categories known as stellar population 1 and stellar population 2. These populations, first identified in the Milky Way, are also clearly evident in Andromeda. Population 1 stars are younger stars, typically under a few billion years old. Are metal-rich, meaning they contain heavier elements like carbon, oxygen, and iron. Astronomers refer to all elements heavier than helium as metals. Are mostly found in spiral arms and galactic disks. Tend to be hotter and bluer, including massive O-type and B-type stars. Are associated with ongoing star formation and nebulae. Population 2 stars are older stars, often over 10 billion years old. Are metal poor, meaning they formed in the early universe when heavy elements were rare. Are commonly found in galactic halos, bulges, and globular clusters. Tend to be cooler and redder, including red giants and horizontal branch stars. Andromeda, like the Milky Way, contains both populations, each occupying distinct regions and serving as historical markers of different phases in the galaxy's evolution. The spiral arms, cradles of stellar youth. If you were to fly above the Andromeda Galaxy and look down at it from space, you'd be struck by its two prominent spiral arms, gracefully winding structures packed with young, luminous blue stars. These arms aren't static, they're more like density waves that trigger star formation as they pass through the galaxy's disk. Characteristics of spiral arm stars. A high-mass, short-lived stars like O-type and B-type main sequence stars dominate the visible light from the arms. These stars can be up to 100,000 times more luminous than our Sun. A star-forming nebulae like HII regions, ionized by the radiation of newborn stars, glow with a soft red or pink hue in telescope images. These regions often harbor open star clusters, collections of dozens to thousands of stars that form together from the same molecular cloud. Because massive stars live fast and die young, often in supernova explosions, the spiral arms are not just nurseries, but also the death grounds of many of the galaxy's most dramatic stellar lives. Interestingly, the presence of hot, young stars in the arms also hints at the availability of gas and dust, raw material that fuels star formation. This shows us that Andromeda is not a static, aging galaxy, but one that still actively builds stars in its disk. The central bulge, an older, redder heart. Moving toward the galaxy's core, we find a very different picture. The central bulge of Andromeda is a dense, spherical swarm of older stars, primarily population 2. These stars are older, redder, and less massive than those in the spiral arms, but they number in the hundreds of billions. Many of them are red giants, stars in the late stages of stellar evolution. These stars have expanded and cooled after exhausting the hydrogen in their cores, becoming bright, reddish-orange beacons of ancient stellar activity. Some notable features of the bulge include a high stellar density, with stars packed tightly together, making it one of the most crowded regions in the entire galaxy. Low rates of star formation, as the available gas has long been consumed or ejected. A presence of metal-poor stars, indicating formation in the early epochs of the galaxy, likely over 10 to 12 billion years ago. A surrounding population of globular clusters, which are gravitationally bound swarms of old stars, some of the oldest objects in the universe. The contrast between the youthful arms and the ancient bulge is a visual timeline of Andromeda's history. The bulge tells the story of the galaxy's birth, while the arms reveal its ongoing evolution. The stellar halo, ghosts of ancient galaxies. Far beyond the bright disk and bulge lies Andromeda's stellar halo, a diffuse, faint, a nearly invisible cloud of stars that stretches for hundreds of thousands of light-years. This region is home to some of Andromeda's oldest and most metal-poor stars, including population 2 red giants, horizontal branch stars, and blue stragglers, older stars that have somehow remained hot and blue, possibly from stellar mergers. But this halo is not just a stellar graveyard, it's also a galactic fossil record. Within it, astronomers have discovered tidal streams of stars, long, looping rivers of light that mark the remnants of dwarf galaxies torn apart by Andromeda's gravity, substructures and stellar overdensities, which suggest multiple merger events in the galaxy's past, are extremely metal-poor stars, some with less than 1/1000th the metallicity of the Sun, truly primordial remnants from the early universe. This halo provides direct evidence that Andromeda grew over time by cannibalizing smaller galaxies, a process that continues to this day. Star clusters in Andromeda. In addition to its field stars, Andromeda is home to over 450 confirmed globular clusters, dense, spherical collections of old stars. Some of these clusters rival or even exceed the mass of the most massive globulus in the Milky Way. These clusters are typically composed of population 2 stars, orbit far above and below the galaxy's disk, formed more than 10 billion years ago, shortly after the galaxy itself, provide valuable insight into the formation timeline of Andromeda. Andromeda also has open clusters in its spiral arms, though these are younger and less massive, and often disperse after a few 100 million years. What the stars reveal about Andromeda's history. The diversity in Andromeda's stellar populations tells a story that stretches across cosmic time. The metal-poor halo stars and globular clusters hint at the galaxy's earliest formation, during an era when the universe was still young and chaotic. The old, red stars in the bulge show us a time when Andromeda was maturing, forming a stable, central core. The blue, metal-rich stars in the arms indicate a continuing process of star birth, fueled by mergers and interactions that stirred up gas and reignited stellar creation. Each stellar population is like a chapter in a long galactic autobiography, and by studying the chemical compositions, motions, and ages of these stars, astronomers can reconstruct the chronology of galactic assembly, how Andromeda became the giant spiral we see today. So, when we gaze at Andromeda in the night sky, whether through a telescope or just with the naked eye, we're not just seeing a single population of stars. We're seeing a symphony of stellar lifetimes. The newborns, glowing hot and blue in the spiral arms. The seasoned elders, glowing red in the bulge and halo. The ancient ancestors, still lingering in globular clusters and stellar streams. Each of them whispers secrets about the formation of the universe, the mechanics of galaxies, and perhaps even our own fate as Andromeda and the Milky Way slowly spiral toward one another. Now that we've unraveled the rich tapestry of Andromeda's stellar populations, from ancient red giants in its halo to the hot, young stars lighting up its spiral arms, it's time to dive even deeper into the engines that power galactic growth, star formation and nebulae. Star formation is a crucial aspect of a galaxy's life cycle, and Andromeda is no exception. While it might not be a blazing beacon of stellar birth like some starburst galaxies in the distant universe, Andromeda still actively forms stars, and it does so in ways that echo the behavior of our own Milky Way, while also revealing intriguing differences. Where stars are born, the spiral arms. If you imagine Andromeda as a cosmic pinwheel, and you should, given its elegant spiral structure, its arms are the zones where gas, dust, and gravity converge to spark star formation. These arms are not solid structures but rather waves of higher density that compress material as they rotate through the galaxy's disk. As interstellar gas clouds move into these denser regions, they get compressed. If the conditions are right, if the gas is cold enough and dense enough, the clouds collapse under their own gravity, fragmenting into clumps that eventually become protostars. Over millions of years, these protostars ignite into nuclear burning stars, releasing heat and light as they stabilize into various stellar classes. Andromeda's spiral arms are actively forming stars, but the rate is relatively moderate, not extreme, yet steady. The largest, most vibrant of these regions contain massive O and B-type stars, which are both short-lived and incredibly luminous. Their radiation not only lights up their surroundings, but also sculpts the interstellar medium, influencing further star formation. Nebulae in Andromeda. The cosmic nurseries. Key to the process of star birth are the nebulae, vast clouds of gas and dust that pepper Andromeda's spiral arms like glowing cosmic cocoons. There are several types of nebulae in Andromeda, each playing a different role in the stellar life cycle. 1. Emission nebulae, HII regions. These are perhaps the most iconic star-forming regions, glowing with a reddish hue due to ionized hydrogen, hence HII. These nebulae are ionized by the ultraviolet light of young, hot stars. A prime example in Andromeda is NGC 206, a massive star-forming complex located in one of its spiral arms. NGC 206 is one of the brightest and largest known OB associations, a grouping of massive, young O and B-type stars, in the local group of galaxies. The presence of such nebulae in Andromeda signals active stellar birth, although at a moderate pace compared to early epochs in the galaxy's life. 2. Reflection nebulae. These clouds of dust don't emit light on their own, but rather reflect the light of nearby stars, usually appearing bluish because of how dust scatters shorter wavelengths more effectively. In Andromeda, these reflection nebulae are often found near young star clusters. Their presence tells us about the distribution of dust and how light from young stars interacts with their surroundings. 3. Dark nebulae. These are cold, dense clouds of gas and dust that block the light from stars behind them. Although they don't shine, they are often the true cradles of star formation. These nebulae contain molecular hydrogen, H, the raw fuel for star creation. Over time, gravity pulls parts of these clouds together, forming dense cores that may collapse into new stars and planetary systems. Many of these dark nebulae have been imaged in infrared wavelengths using instruments like the Spitzer Space Telescope, which can peer through the dust to reveal the early stages of star birth hidden inside. Star formation rate, SFR, in Andromeda versus the Milky Way. Let's now compare the pace of star formation in Andromeda with that of our own galaxy. Andromeda's star formation rate are estimated at about 0.4 to 1 solar masses per year, meaning it forms the equivalent mass of roughly 1 sun per year, or slightly less. This is relatively modest, considering its size and stellar population. In fact, recent studies suggest that Andromeda is in a declining phase of star formation, perhaps entering a quieter stage of galactic evolution, often referred to as quenching. Milky Way's star formation rate are higher than Andromeda's, at roughly 1.5 to 2 solar masses per year. The Milky Way is still vigorously forming stars, particularly in regions like the Orion Arm, home to the Orion Nebula and other stellar nurseries. This suggests that while both galaxies are spiral in shape and compositionally similar, they are at different evolutionary stages. So why the difference? Astronomers believe that Andromeda may have experienced a more intense past. Its earlier merger events and internal dynamics might have used up or dispersed much of its available cold gas. Alternatively, feedback from supernovae or its central black hole may have heated or blown out gas that would otherwise have formed stars. Environmental factors affecting star formation in Andromeda. Andromeda's environment and past interactions play a major role in shaping its star-forming behavior. Gravitational interactions. Encounters with satellite galaxies like M32 and M110 may have disturbed gas clouds, compressing some regions, triggering star formation, while stripping others, suppressing it. Air bar dynamics. Andromeda's central bar may be funneling gas toward the core, altering star formation patterns across the disk. Age and evolution. At an estimated age of 9 to 10 billion years, Andromeda may simply be maturing past its most fertile years, like a tree that once bloomed heavily but now produces less fruit each season. The role of star clusters. Andromeda's star-forming regions also give rise to open clusters, loose groups of stars formed from the same nebula. These clusters typically remain gravitationally bound for a few 100 million years before dispersing. They serve as stellar laboratories, where astronomers can study stellar evolution in stars of the same age but varying mass. Examples include the many young star clusters embedded in NGC 206, which have been extensively studied with telescopes like Hubble and Spitzer. A quiet giant or a sleeping powerhouse. Though Andromeda's current star formation activity is relatively low, astronomers believe it's not done yet. Given the reservoirs of gas and the potential for future interactions, especially the coming merger with the Milky Way, its star formation rate could spike again in the distant future. When galaxies interact or collide, they often compress gas clouds on massive scales, igniting waves of starbirth. So while Andromeda may seem quiet now, it's likely only between acts in a much longer cosmic play. A living galaxy. In essence, Andromeda is not a static collection of stars and gas. It's a living, breathing structure, continually cycling material from gas to stars and back again through stellar winds, supernovae, and galactic dynamics. Its active star-forming regions, though fewer than in its youth, still glow with the light of new creation, reminding us that even in cosmic terms, maturity doesn't mean stillness, it means change. Andromeda may be more measured in its pace now, but its nebulae continue to birth stars, its arms continue to foster growth, and its history is still being written in starlight. Let's now journey into one of the most fascinating and mysterious components of the Andromeda Galaxy, a force so powerful, it defies our everyday understanding of space and time, the supermassive black hole at Andromeda's heart. At the core of nearly every massive galaxy lies a supermassive black hole, an astronomical behemoth with a mass ranging from millions to billions of times that of our Sun. Andromeda is no exception. Nestled deep within its central bulge, hidden behind clouds of stars, dust, and gas, lies a silent giant, a black hole known as Andromeda's central supermassive black hole, officially designated as M31*, pronounced M31 star. How massive is it? The supermassive black hole at the center of the Andromeda Galaxy is estimated to be between 100 million and 140 million solar masses, that is, 100 to 140 million times the mass of our Sun. To put that in perspective, the black hole at the center of our own Milky Way, Sagittarius A*, has a mass of about 4 million solar masses. That means Andromeda's central black hole is more than 25 times as massive as the one in our galaxy. Despite this incredible mass, it doesn't dominate the entire galaxy. Remember, Andromeda is home to about 1 trillion stars, not to mention massive amounts of dark matter and interstellar gas. Still, this black hole plays a vital role in the dynamics of the galactic center. A quiet giant. Interestingly, even though Andromeda's central black hole is so massive, it's currently not very active. In astronomy, we often refer to such black holes as being in a low-luminosity active galactic nucleus, AGN, state, or more simply, dormant or quiescent. So what does that mean? It means that, at present, the black hole isn't actively feeding on large amounts of matter. There's no enormous accretion disk glowing brightly in X-rays, no massive relativistic jets blasting out into space, and no huge clouds of material being ripped apart at the event horizon. Instead, it's relatively quiet, sitting there like a sleeping volcano. However, just because it's quiet now doesn't mean it always was, or always will be. Galactic centers can fluctuate between active and dormant phases, depending on how much matter, gas, stars, or even smaller black holes fall into their gravitational grip. How do we know it's there? If the black hole is so quiet, how do we even know it exists? Astronomers have detected it by observing the motion of stars in the innermost regions of Andromeda. Using spectroscopic data and high-resolution imaging, especially from the Hubble Space Telescope, scientists have tracked how stars orbit the central bulge. These stars move incredibly fast, much faster than would be expected if the core were composed solely of visible stars and gas. By analyzing their velocities and orbital patterns, researchers can infer the presence of a very massive but invisible object. The only explanation consistent with the data is a supermassive black hole. One particularly fascinating discovery came from a team using Hubble in the late 1990s and early 2000s. They found that the nucleus of Andromeda is actually double, meaning it has two distinct brightness peaks, known as P1 and P2. This was puzzling at first, but further study revealed that this wasn't two black holes, it was an asymmetric disk of stars orbiting the central black hole, forming what appears to be a double nucleus due to our angle of view and the way light is distributed. At the heart of this unusual stellar structure lies the true gravitational center, the supermassive black hole. What does a dormant black hole do? Even when not actively accreting matter, a supermassive black hole still exerts an enormous gravitational influence on its surroundings. In the case of Andromeda, it affects the orbits of stars within a few light-years of the core. It likely helped shape the bulge of stars surrounding it. It may regulate star formation in the central regions by heating or displacing gas, even during past active phases. Black holes are also theorized to self-regulate their host galaxies. During active periods, when a black hole is consuming lots of matter, it can emit powerful winds and radiation that blow away gas, effectively shutting down future star formation. This feedback process is thought to be one reason galaxies stop forming new stars after a certain point. Andromeda may have experienced such a phase in its distant past, which could help explain its current lower star formation rate compared to the Milky Way. Where did Andromeda's black hole come from? Supermassive black holes are believed to form relatively early in a galaxy's life. There are several theories about their origins. 1. Direct collapse of massive gas clouds in the early universe, forming black holes thousands of times the mass of the Sun almost immediately. 2. Growth from stellar mass black holes, which merge and consume matter over billions of years. 3. Mergers of galaxies, which often bring together the black holes from two galactic centers, ultimately forming a larger black hole through gravitational interactions and eventual coalescence. Andromeda's black hole likely grew through a combination of these processes. It has probably consumed numerous stars, gas clouds, and perhaps even other black holes brought in by satellite galaxies, such as M32 or M110, as they spiraled inward over cosmic time. The role of the black hole in the future Milkomeda. Looking billions of years into the future, when Andromeda collides and merges with the Milky Way, the two central black holes, M31* and Sagittarius A*, are expected to spiral toward one another due to dynamical friction. Eventually, they will merge into a single, even more massive black hole at the heart of the new galaxy, which scientists have nicknamed Milkomeda. This future black hole would likely weigh in at hundreds of millions of solar masses and could produce gravitational waves detectable by next-generation instruments. It might even enter a brief but bright active phase, consuming the chaos of gas and dust stirred up by the collision, before settling once again into a quiet slumber at the center of the new galaxy. A cosmic anchor. In many ways, the supermassive black hole at the center of Andromeda is like a cosmic anchor, a dense, immovable force that quietly holds the galaxy's central dynamics together. Though invisible to the naked eye and undetectable without advanced instruments, it serves as a reminder of the extreme forces that govern the universe. A place where physics breaks down as we know it, where even light cannot escape, and where time and space are warped beyond recognition. Andromeda's black hole may not currently roar with power or emit dazzling jets of radiation, but it is nonetheless a monumental presence, silent, heavy, and awe-inspiring. Let's now step into the shadows of the universe, into a realm that defies our understanding of matter, light, and gravity. While we've explored the glowing stars, nebulae, and the black hole at the heart of Andromeda, there's something far more elusive and pervasive that holds the galaxy together, something that doesn't emit or reflect any light: dark matter. The mystery of dark matter. Imagine trying to solve a puzzle where 90% of the pieces are invisible. That's what astronomers face when they study galaxies like Andromeda. Most of what makes up a galaxy, its visible stars, glowing nebulae, and even the central supermassive black hole, accounts for only a tiny fraction of its total mass. The rest. It's something we cannot see, cannot touch, and cannot directly detect, yet we know it's there because we can observe its gravitational effects. This invisible material is what scientists call dark matter. Dark matter does not interact with electromagnetic radiation, meaning it doesn't emit, absorb, or reflect light. That's why we call it dark. It's not dark like the night sky. It's completely transparent, completely undetectable by normal instruments. The only way we know it exists is because of the gravitational influence it exerts on visible matter. Why do we think Andromeda has dark matter? The biggest clue comes from a phenomenon known as the galactic rotation curve. In the early 20th century, astronomers began mapping the rotation speeds of stars and gas in spiral galaxies like Andromeda. According to Newtonian physics, the further a star is from the center of a galaxy, the slower it should move, just like planets in our solar system. Mercury orbits quickly because it's close to the Sun, while Neptune creeps slowly around the edge. If galaxies were made only of visible matter, their stars should follow this same pattern. But here's the twist: they don't. When scientists like Vera Rubin studied galaxies such as Andromeda in the 1970s, they discovered something strange. Instead of slowing down, the stars on the outer edges of Andromeda's disk were moving just as fast as those near the center. This defied all expectations. It was as if something invisible was pulling on those stars, holding them in orbit, something with mass, but no light. This missing mass was dark matter. Dark matter's role in holding Andromeda together. If Andromeda only contained the mass we can see, its stars, gas, dust, and central black hole, it wouldn't have enough gravity to keep its outer stars from flying off into space. In fact, based on visible matter alone, Andromeda's disk should tear itself apart at the speed its outer stars are rotating. The only explanation is that Andromeda has an enormous halo of dark matter, a spherical, invisible cloud of mass that extends well beyond the edges of the visible galaxy. This dark matter halo acts like a gravitational glue, binding the galaxy together and allowing it to rotate the way it does. Estimates suggest that over 80% of Andromeda's total mass is dark matter. That means for every kilogram of normal, baryonic matter, stars, gas, dust, there are at least 4 kilograms of dark matter. Without dark matter, galaxies like Andromeda wouldn't exist in the form we know them. What is this dark matter made of? That's the golden question, and it's one of the biggest unsolved mysteries in all of astrophysics. We don't yet know what dark matter is, but scientists have developed several leading hypotheses. 1. WIMPs, weakly interacting massive particles, hypothetical particles that are massive but interact only via gravity and the weak nuclear force, not electromagnetism, making them invisible to light. 2. Actions, ultralight particles that might make up dark matter in large quantities. 3. Machos, massive compact halo objects like black holes, neutron stars, or brown dwarfs that could exist in great numbers in the halos of galaxies. But this idea has largely fallen out of favor due to lack of evidence. Despite years of research, no one has directly detected a dark matter particle. We only infer its existence by its gravitational effects on galaxies like Andromeda. Gravitational lensing and dark matter maps. Another method astronomers use to study dark matter in Andromeda is gravitational lensing. Einstein's theory of general relativity tells us that mass bends spacetime, and therefore, bends light. When light from a more distant object passes near a massive galaxy like Andromeda, it gets distorted. By studying these distortions, astronomers can map the distribution of mass, including the dark matter halo. Using this technique, researchers have confirmed that Andromeda's mass extends far beyond its visible disk, forming an immense dark halo that plays a central role in its gravitational structure. Simulations and the cosmic web. When scientists simulate the formation of galaxies in a universe without dark matter, the results look nothing like the real universe. But when they include dark matter, especially cold dark matter, which moves slowly and clumps easily, the simulations begin to match what we observe. Andromeda, in these simulations, forms as part of a cosmic web, a vast network of dark matter filaments stretching across the universe. These filaments are the scaffolding of structure, with galaxies forming at the intersections, where dark matter pools and concentrates. So, Andromeda didn't form in isolation. It was pulled together by dark matter, shaped by it, and continues to be dominated by it. Dark matter and the local group. Dark matter also plays a role in how Andromeda interacts with its cosmic neighbors, including the Milky Way. Both galaxies are the dominant members of the local group, a gravitationally bound collection of over 50 galaxies. The mutual gravitational pull between the Milky Way and Andromeda isn't just due to their visible mass, it's their massive dark matter halos interacting that set them on a collision course. The invisible halos are already touching or overlapping, millions of years before the visible galaxies themselves will collide. This dark matter bridge, though unseen, is pulling the galaxies together, guiding them toward their ultimate merger billions of years from now. Andromeda as a dark matter laboratory. Because Andromeda is so close and so massive, it serves as a natural laboratory for studying dark matter. By examining the motion of stars and gas at different radii, the gravitational lensing of background objects, the interaction between Andromeda and its satellite galaxies, and the detailed structure of its halo, astronomers can refine their models of dark matter's behavior on galactic scales. Every data point collected from Andromeda adds another piece to the cosmic puzzle, helping us understand not only our neighboring galaxy, but also the unseen 85% of the universe. The ongoing search. The quest to understand dark matter continues, with ground-based observatories, space telescopes, and underground particle detectors all playing a part. Andromeda, with its rotating stars, extended halo, and intricate gravitational dynamics, stands as a silent witness to this mystery. It's a galaxy of light, but also a galaxy of shadow, home to stars and darkness in equal measure. One day, perhaps we'll identify the true nature of dark matter. But until then, Andromeda will continue to challenge, inspire, and illuminate the greatest unanswered questions in astrophysics. Let us now leave behind science for a moment and step into the world of legends and ancient stories, where the night sky wasn't just a map of stars and galaxies, but a canvas of myths, heroes, and gods. As we explore the mythology behind the Andromeda Galaxy, we find that it's not just a name for a distant, colossal spiral of stars. It's a window into the human imagination, one that has inspired storytellers, astronomers, poets, and philosophers for millennia. Andromeda in mythology, a princess among the stars. The Andromeda Galaxy takes its name from a figure in Greek mythology, Princess Andromeda, the daughter of King Cepheus and Queen Cassiopeia of Ethiopia. Her story is both tragic and heroic, filled with divine wrath, sacrifice, and redemption. It's one of the most enduring legends from antiquity, and it's deeply woven into the stars. Queen Cassiopeia, according to myth, was a woman of unmatched beauty, but also of overwhelming vanity. She dared to boast that she and her daughter Andromeda were more beautiful than the Nereids, the sea nymphs who accompanied Poseidon, the god of the sea. Angered by this insult to his divine companions, Poseidon sent a monstrous sea creature, sometimes identified as Cetus, to ravage the coast of Ethiopia. To appease the gods and save their kingdom, Cepheus and Cassiopeia were told by the oracle of Ammon that they must sacrifice Andromeda to the sea monster. So, in a heartbreaking act of obedience, Andromeda was chained to a rock by the sea, left to be devoured. But just as the monster approached, a hero arrived, Perseus, son of Zeus and the mortal Danae. Fresh from his conquest of the Gorgon Medusa, whose gaze turned creatures to stone, Perseus saw Andromeda, fell in love instantly, and struck a deal with her parents. He would rescue her if he could claim her as his wife. Using Medusa's severed head, Perseus turned the sea monster to stone and freed Andromeda. The two married and went on to have a son, Perses, who according to some myths became the ancestor of the Persian people. From myth to constellation. As a tribute to their story, the gods immortalized them in the stars. You can still find Andromeda, Perseus, Cassiopeia, Cepheus, and even Cetus, the sea monster, as constellations in the night sky. It is one of the most complete celestial mythologies, an entire mythological saga laid out above us, visible during the autumn months in the northern hemisphere. The Andromeda constellation, in particular, is where the Andromeda Galaxy, M31, is located. It's poetic, really. The galaxy that bears her name lies within the same star group that ancient humans imagined was her celestial throne. The stars, once used to tell tales of gods and monsters, now guide us to a neighboring island universe. This blending of myth and astronomy is not accidental. For thousands of years, human beings have looked up at the night sky and projected their stories onto the stars. Before science gave us telescopes and spectral analysis, the sky was our storybook. Constellations were not only tools for navigation and timekeeping but anchors for imagination and meaning. Cultural storytelling across the ages. While the Greek tale of Andromeda is the one most associated with the galaxy's name in Western astronomy, myths involving chained women, sea monsters, and heroic rescues appear in many cultures. For example, in some Babylonian myths, similar stories of celestial punishment and redemption are told through stars. The Hindu traditions assign different meanings and deities to the constellations in that part of the sky, weaving their own cosmic narratives. In Chinese astronomy, the stars that form the Andromeda constellation were part of multiple asterisms, smaller groupings of stars with different names and meanings altogether. What unites all these traditions is a deep human tendency to interpret the stars as more than just distant suns. We saw in them our gods, our fears, our ideals, and our stories. And it is precisely this poetic inclination that led us to name a galaxy, something we could never have seen with the naked eye in ancient times, after a legendary princess from myth. The symbolism of Andromeda. The myth of Andromeda is rich with symbolism that continues to resonate even today. A sacrifice and innocence, Andromeda was punished not for her own actions, but for her mother's vanity. Her story explores the theme of innocent suffering, a motif found across cultures and epochs. A heroism and love. Perseus's act of heroism is a tale of love at first sight, but also of courage and cleverness. His use of Medusa's head is symbolic of the idea that intelligence and wisdom can defeat brute force. A transformation and immortality. The transformation from mortal to celestial form, being placed in the sky, is a common reward in Greek mythology, representing immortality through memory. The constellation and galaxy named after her ensure that Andromeda's story endures. In this way, the Andromeda Galaxy is more than just a collection of stars, gas, and dark matter. It is a symbol of humanity's timeless quest for meaning, of our ability to weave myth with science, imagination with observation. Astronomy and myth, a shared legacy. It's interesting to consider that even in the modern age of space telescopes and astrophysics, we still name celestial bodies after mythological figures. Why? Because science and storytelling are not opposites, they are complementary. Where science asks what is this? And how does it work? Mythology asks what does this mean? And why do we care? By naming a galaxy after a myth, we link our ancestors' poetic view of the cosmos with our modern scientific understanding. It's a bridge between the past and the present, between art and science. So, when you look up into the night sky on a crisp autumn evening and locate the faint smudge that is the Andromeda Galaxy, you're not just looking at another galaxy. You're looking at a legend, a symbol of rescue and redemption, immortalized in the heavens. Andromeda's enduring allure. There's something deeply human in this tradition of linking celestial objects with mythology. It shows that no matter how advanced our technology becomes, we are still storytellers at heart. The Andromeda Galaxy, now studied with cutting-edge instruments, satellite observatories, and spectral analysis, was once just a mysterious smudge in the sky, and before that, a myth waiting to be told. And in some sense, it still is. Now that we've explored the mythological resonance behind Andromeda's name, it's time to return to its physical reality, one that is just as dramatic, though in a very different way. When we observe the Andromeda Galaxy not through the lens of legend, but through the eyes of modern astronomy, we find a cosmic history marked by collision, assimilation, and transformation. Galaxies are not static objects. They are dynamic ecosystems of stars, gas, dust, and dark matter, constantly influenced by gravity and shaped by interaction. Andromeda's grand spiral structure, its starry arms stretching across more than 220,000 light-years, did not form in isolation. Its size, complexity, and mass all hint at a violent and active history, one that includes the absorption of smaller galaxies, the distortion of stellar orbits, and the blending of once separate populations of stars. This is the story of galactic cannibalism, and Andromeda is a prime example. The tale told by tidal streams. One of the clearest indicators that Andromeda has merged with smaller galaxies in its past is the presence of tidal streams, faint, ribbon-like structures of stars and stellar debris that stretch around the galaxy. These aren't random features. They are the cosmic fingerprints left behind by dwarf galaxies that strayed too close to Andromeda and were shredded apart by its immense gravitational pull. In fact, deep sky surveys, particularly those conducted with powerful telescopes like Subaru, Keck, and the Hubble Space Telescope, have revealed numerous such streams looping around Andromeda. These include the giant stellar stream, perhaps the most striking tidal feature. This massive arc of stars extends over 100,000 light-years and is thought to be the remains of a dwarf galaxy that collided with Andromeda around 700 million years ago. Its trajectory, velocity, and composition suggest it was once a small, independent galaxy now completely assimilated. Other shells and loops surrounding Andromeda's halo are multiple shell-like structures and arcs of stars, evidence of past galactic mergers. These shells are the remnants of stellar populations that were flung into extended orbits and slowly decayed into Andromeda's gravitational grip. These features are invisible to the naked eye, but they are clearly mapped in long-exposure astrophotography and computer-modeled simulations, which help reconstruct the ancient dance of destruction that gave rise to Andromeda's current shape. Unusual stellar populations and asymmetries. Another hint that Andromeda has a collision-filled past comes from the analysis of its stellar populations and their distributions. In a pristine spiral galaxy, you would expect a fairly symmetrical distribution of stars, both in age and composition, especially across the spiral arms. However, Andromeda shows distortions and asymmetries. Lopsided spiral arms. Andromeda's spiral arms are not perfectly symmetrical, and some appear stretched or warped, possibly due to gravitational interactions with past dwarf galaxies, or even its current satellites, like M32 and M110. Older stars in unexpected regions. Astronomers have detected older, metal-poor stars, typically found in the halo or bulge, in regions of the disk, suggesting that those stars didn't form there. Instead, they were likely injected during the disruption of a smaller galaxy, whose stars were deposited throughout Andromeda's structure. As substructures in the halo, the galaxy's stellar halo, which stretches far beyond its visible arms, is populated with clumps and streams that don't fit into a smooth spherical distribution. These clumps are relics of satellite galaxies that were partially assimilated, leaving behind distinct, localized populations of stars. All these anomalies speak to a history of dynamic evolution, of Andromeda growing by devouring smaller galaxies, pulling them in over billions of years, and incorporating their stars into its own vast system. Simulations and modeling galactic cannibalism. Thanks to advanced simulations using supercomputers and gravitational modeling software, astronomers can now rewind the clock and simulate what Andromeda might have looked like millions or even billions of years ago. These simulations, fed with observational data, allow us to virtually see how different mergers likely occurred. One landmark study led by researchers using data from the PANDAS, Pan-Andromeda Archaeological Survey, project showed that Andromeda had undergone at least two major merger events in the last 8 billion years. 1. A massive merger around 2 billion years ago. Simulations suggest that Andromeda may have merged with a fairly large galaxy, significantly larger than a typical dwarf galaxy, contributing to the thickening of its disk, the warping of its spiral arms, and a starburst phase. 2. Multiple minor mergers over time. The steady stream of smaller galaxies over cosmic time, some already known like the progenitor of the giant stellar stream, further shaped its outer halo and introduced new stellar populations, each with unique velocities and chemical signatures. These findings are significant because they indicate that even galaxies as seemingly stable and elegant as Andromeda are shaped by cosmic chaos, and that their grandeur today is the product of violent, transformative interactions. Evidence in globular clusters. Another piece of the puzzle comes from Andromeda's globular cluster system. Globular clusters are dense, spherical groups of very old stars that orbit the cores of galaxies. Andromeda boasts more than 450 globular clusters, more than twice the number found in the Milky Way. But here's the interesting part. Some of these globular clusters have unusual orbits and compositions, suggesting that they were not originally part of Andromeda. Instead, they were imported from satellite galaxies, torn away during mergers and now serving as time capsules of those galactic encounters. These clusters give astronomers valuable insights into the galaxies Andromeda has consumed, acting like fossil records of ancient mergers. Why this matters? Understanding Andromeda's merger history is not just about studying one galaxy. It serves as a template for understanding galactic evolution across the universe. The universe is filled with billions of galaxies, and almost all of them grow by merging with others. Andromeda, being relatively close and well resolved by our telescopes, offers us a front-row seat to this process. It also has direct implications for us. Andromeda and the Milky Way are on a collision course, a future cosmic merger that we will explore in an upcoming segment. Knowing what happened in Andromeda's past gives us clues about what might happen in our own galactic future. A dynamic portrait of a galaxy. So, when we look at the majestic spiral arms of Andromeda through a telescope, we must remember, this is not a static portrait. It's a snapshot of a dynamic life, a galaxy that has grown by cosmic assimilation, stretched by gravity, and sculpted by time. Its present form is an echo of its past violence, and a prelude to an even more dramatic future. The tidal streams, the disrupted star fields, the odd orbits, all of them whisper the same thing. Andromeda is a survivor of galactic collisions, and it carries the scars to prove it. As we leave behind Andromeda's chaotic past filled with mergers and cannibalized galaxies, we now turn our gaze to a profound reality that affects not only Andromeda but also us, here on Earth. It's a reality that brings an otherwise distant and serene swirl of stars much closer to home. You see, Andromeda isn't just a fascinating subject for astronomers to study in isolation. It's not merely some massive structure sitting peacefully 2.5 million light-years away, frozen in the vast blackness of the universe. No, Andromeda is moving. And not just moving, it's heading straight for us. Andromeda's motion, the great cosmic approach. Let's start with a simple but astonishing fact. The Andromeda Galaxy is hurtling through space directly toward the Milky Way at a speed of about 110 kilometers per second, or roughly 400,000 kilometers per hour. To give some scale to that, in just 1 hour, Andromeda moves closer to us by a distance greater than the entire circumference of Earth. Now, you might be wondering, how do we know this? The answer lies in a phenomenon called the Doppler effect. This is the same principle that causes the pitch of a siren to change as an ambulance passes by. In astronomy, the Doppler effect alters the wavelength of light depending on whether an object is moving toward or away from us. When an object moves away, its light stretches into longer wavelengths. This is called redshift. When an object moves toward us, its light compresses into shorter wavelengths. This is called blueshift. Andromeda's light is blueshifted, meaning that instead of being pushed away from us like most other galaxies in the universe, it is approaching us. This is not only fascinating, it's incredibly rare. A galactic exception, moving against the flow. Most galaxies in the observable universe are moving away from each other. This is due to the overall expansion of the universe, a phenomenon first described by Edwin Hubble in the early 20th century. In general, the farther away a galaxy is, the faster it is receding from us, a relationship known as Hubble's law. So why is Andromeda different? The answer lies in gravitational binding. Andromeda and the Milky Way are the two largest galaxies in what's called the local group, a small cluster of galaxies about 10 million light-years across. Other members include the Triangulum Galaxy, M33, various dwarf galaxies like Leo I and II, and of course, Andromeda's own satellites M32 and M110. Within this local group, gravitational interactions dominate over cosmic expansion. The gravitational pull between massive galaxies like the Milky Way and Andromeda is strong enough to overcome the expansion of space at their distance. Essentially, gravity has caught them in each other's embrace, and they are now spiraling toward a cosmic collision. This blue-shifted movement was one of the first observational clues astronomers had that not all galaxies obey the large-scale flow of the universe. Andromeda is not a part of the universe's general outward expansion. It's part of a gravitationally bound system that's fated to evolve in a dramatically different way. Precision measurements, a complex dance. Although we've known for decades that Andromeda is approaching us, recent advances have added far more detail to the picture. Thanks to the Hubble Space Telescope and advanced astrometric instruments like the Gaia Space Observatory, astronomers have been able to measure not just Andromeda's approach velocity, but also its motion across the sky, its so-called tangential velocity. This was a monumental breakthrough. For a long time, we only knew the radial velocity, how fast Andromeda is moving toward or away from us. But measuring its sideways motion allows us to predict the angle and outcome of the eventual collision. What scientists have found is that while Andromeda is approaching head-on to a large extent, it also has a slight sideways motion. This means the galaxies may not collide in a perfectly central impact, but they will still merge, just with a bit of a cosmic glancing blow rather than a direct hit. Simulations of this interaction, using data from Hubble and Gaia, allow astronomers to virtually watch the future unfold in detail, something we'll dive into more fully in the next segment. Implications of the approach. The fact that Andromeda is on a collision course with the Milky Way is more than just a cosmic curiosity. It's a reminder that galaxies are not static structures. They are dynamic, evolving, and sometimes doomed to merge through the invisible hand of gravity. For Andromeda and the Milky Way, their mutual gravitational attraction is pulling them together in an unstoppable embrace, one that will climax in a galactic merger in about 4 to 5 billion years. Let's briefly think about what that means in cosmic terms. Today, we see Andromeda as a beautiful spiral galaxy in the sky, visible as a faint smudge with the naked eye on a dark night. In 2 billion years, it will appear much larger in our sky as it draws nearer, eventually dominating the celestial sphere with a dazzling display of stars. By 4 to 5 billion years from now, the collision will begin in earnest. Stars will pass by one another at vast distances. Remember, stars are incredibly far apart, but gravitational forces will distort both galaxies, triggering massive waves of star formation, gas redistribution, and structural change. But don't worry, we'll go into the full dramatic detail of that future in the next section. A front-row seat to cosmic mechanics. Perhaps the most profound part of this reality is that we, here on Earth, get a front-row seat to this grand event. We are not simply bystanders in an isolated galaxy, we are part of a larger cosmic dance, and Andromeda is our partner. In this dance, we are now approaching the part where the two dancers circle each other more tightly, gravity pulling them in, momentum carrying them forward, the the stage set for a breathtaking finale. Astronomers around the world, using radio telescopes, optical observatories, and space-based instruments, continue to monitor this approach. Every new measurement helps refine our understanding of how this galactic merger will unfold, how it has already begun in subtle gravitational ways, and how it will reshape the very identity of our night sky. So next time you gaze at the Andromeda Galaxy, either through a telescope or as a ghostly smear of light on a moonless night, remember, it's coming for us. Not with menace, but with inevitability, a gravitational encounter written into the very fabric of space-time billions of years ago. It's not just a distant object in space. It's our future, an enormous, radiant spiral of stars slowly falling into our sky. In the vast stillness of cosmic time, galaxies collide with the same inevitability as sunsets follow day. And for us, one of the most remarkable and monumental of these cosmic ballets is already in motion: the future collision of the Andromeda Galaxy with our own Milky Way. It's a staggering idea, not a science fiction fantasy, but a scientifically verified event, that the two largest galaxies in the local group are on a direct path toward one another. This galactic encounter is already scripted by gravity, unfolding slowly over billions of years. So, what happens when two massive spiral galaxies, each with hundreds of billions of stars, gas clouds, dust lanes, dark matter halos, and perhaps even countless civilizations, collide head-on? Let's walk through it. Timeline: a slow-motion dance. The collision between Andromeda and the Milky Way isn't going to happen tomorrow, or next year, or even within the lifetime of our planet's remaining geological epochs. This is a 4.5 billion-year process, a slow, elegant waltz on cosmic timescales. Here's what scientists currently predict. 2 billion years from now, Andromeda will appear much larger in our night sky. What is now a faint smudge visible only on very dark nights will become an enormous glowing spiral, stretching across the heavens. Earth, by then, may be unrecognizable, perhaps devoid of life if the sun has become too hot for stable ecosystems. 4 billion years from now, the outer halos of the two galaxies will begin to interact. Tidal forces will start to stretch their spiral arms. This phase is called the first pass. As the galaxies graze each other, stars will be flung into elongated streams, and massive bursts of star formation will be triggered as gas clouds collide and compress. 4.5 billion years from now, the galaxies will eventually merge in earnest. Over a series of interactions and gravitational pulls, called dynamical friction, their motions will slow and settle. After several close encounters, the central bulges will coalesce. What will remain is not a spiral galaxy anymore, but something entirely new. Birth of Milkomeda. The final product of this grand merger is a new, larger galaxy, a single, massive elliptical galaxy. Astronomers have nicknamed it Milkomeda, a blend of Milky Way and Andromeda, though it may someday receive a more formal designation. Milkomeda won't have the graceful, pinwheel-like spiral arms we associate with galaxies like the Milky Way and Andromeda. Instead, elliptical galaxies are more rounded, three-dimensional, and featureless, made up of older stars that orbit in random directions. Much of the structure of the original spirals will be blurred and absorbed into the new galactic form. The gas and dust that once fed the star-forming regions in both galaxies will be largely used up during the collision. As a result, Milkomeda will likely not be very active in star formation after the initial merger-induced burst fades. It will be filled with billions of stars, many of them older, redder, and cooler. What happens to Earth? Now, the big question: should we be worried? The answer is no, not in the slightest. Despite the sheer size and scale of the collision, the vast distances between individual stars mean direct collisions are almost impossible. Stars are incredibly small relative to the space between them. Even though the Milky Way contains hundreds of billions of stars, it's also about 100,000 light-years wide, leaving plenty of room for objects to pass by each other harmlessly. So, Earth and the rest of the solar system are not expected to be destroyed. In fact, there's a decent chance that our entire star system will survive the merger more or less intact. That said, the Sun's orbit around the galactic center will be disturbed. Our solar system might be flung into a different region of the galaxy, perhaps even into the outskirts of Milkomeda. It could also be sent on a more erratic orbit, as gravitational influences from new massive stars and black holes tug on it during the merger. But by the time this happens, the Sun itself will be nearing the end of its life. In about 5 billion years, the Sun will expand into a red giant, engulfing Mercury and Venus, and possibly Earth, before shrinking into a white dwarf. So Earth's long-term habitability is already on a countdown, independent of the Andromeda merger. The galactic collision is unlikely to be the cause of our end. It's merely a backdrop to a destiny already written in our star's core. A sky transformed. If Earth or any artificial observatories remain operational during this event, the night sky will look dramatically different. Here's what observers, perhaps robotic, artificial, or even evolved life forms, might see. As Andromeda approaches, it will grow ever larger in the night sky. By about 3.75 billion years from now, it will dominate the sky as a stunning spiral, 5 times the size of the full moon, but faint and hazy, like a ghostly, glowing river of stars. As the first pass occurs, spectacular tidal tails and star streams will appear, long, curling ribbons of stars pulled from both galaxies. In the following billions of years, the sky will fill with the blended remnants of both galaxies. Double cores may appear in the center for some time, as the supermassive black holes of both galaxies orbit one another before merging. Eventually, the night sky will become smoother, with the Andromeda Galaxy's central bulge forming a brighter, more uniform glow. The era of the Milky Way's spiral arms and Andromeda's elegant structure will be gone, absorbed into a vast, merged whole. The supermassive black holes. Another profound event during this galactic collision involves the supermassive black holes at the centers of both galaxies. The Milky Way's Sagittarius A** and Andromeda's central black hole are both several million times the mass of the Sun. During the merger, these two behemoths will spiral toward one another, radiating gravitational waves as they do. Eventually, they will merge into a single, even more massive black hole, potentially one of the most massive known in the local group. This event will likely release an enormous burst of gravitational radiation, warping spacetime in all directions. Though we won't feel this here on Earth in any destructive way, future observatories, like the space-based LISA, Laser Interferometer Space Antenna, might one day detect the ripples in spacetime caused by such an epic event. The fate of the local group. After the merger, Andromeda will likely become the gravitational anchor for the rest of the local group. Other smaller galaxies, such as the Triangulum Galaxy, M33, may be drawn in next. Some astronomers believe M33 could be part of the merger itself, creating a three-way galactic collision. Eventually, Andromeda may evolve into a giant elliptical galaxy, much like those seen at the center of massive galaxy clusters. Its halo of stars, dark matter, and black holes will be immense, encompassing all that once belonged to dozens of smaller galaxies. Looking even farther ahead. Now, zoom out even further. In hundreds of billions of years, assuming no fundamental changes to the laws of physics, galaxies like Andromeda will be the only islands of light left in the observable universe. Due to the accelerated expansion of space, driven by dark energy, distant galaxies will vanish beyond our cosmic horizon. Eventually, Andromeda could be the only galaxy left visible to whatever observers might remain. In this dark, empty cosmos, all that remains will be the merged legacy of two once proud spiral galaxies, our Milky Way and our majestic neighbor, Andromeda. So, when you look up at Andromeda, you're not just seeing a galaxy, you're seeing our future. A future filled with stellar collisions, not of stars, but of galaxies, swirling chaos, breathtaking transformation, and eventual peace in a new elliptical form. The birth of Andromeda is not something to fear, but something to wonder at. It is the next grand chapter in the life story of galaxies. And we, here on Earth, are privileged to know of it, to understand it, and to find our place within it. As the grand narrative of the Andromeda Galaxy unfolds across billions of years and trillions of stars, we are fortunate to be witnessing its story in real time, from a distance of 2.5 million light-years away. For modern science, Andromeda is more than just a distant celestial object, it's a living laboratory. It's a rare chance to study a galaxy similar to our own with incredible clarity. And thanks to both professional observatories and passionate amateur astronomers, Andromeda is no longer just a smudge in the sky, it's a fully realized structure with remarkable complexity. This segment is all about how we observe Andromeda. From the incredible eye of the Hubble Space Telescope to the backyard setups of stargazers around the world, let's explore how humans are peering into the past, present, and future of our cosmic neighbor. A target for all eyes, professional and amateur observers alike. Andromeda is unique in its accessibility. While most galaxies are distant and faint, M31, its catalog name, is visible to the naked eye under the right conditions. That makes it one of the most frequently observed galaxies by amateurs with binoculars and professionals wielding billion-dollar telescopes. This galaxy is regularly observed across multiple wavelengths: visible light, infrared, ultraviolet, X-rays, and even radio waves. Each spectrum unlocks a different secret, helping scientists understand the structure, star formation, motion, and chemical composition of Andromeda. While professional observatories offer high-resolution data and groundbreaking insights, amateur astronomers also play a vital role, particularly in photometry, wide-field imaging, and long-term monitoring. Let's look at how both communities engage with this galaxy. The Hubble Space Telescope, piercing the darkness. If there's one instrument that has revolutionized our view of the Andromeda Galaxy, it's the Hubble Space Telescope, HST. Orbiting 547 kilometers above Earth, Hubble has no atmosphere to blur its vision. Since its launch in 1990, HST has delivered unprecedented high-resolution images of Andromeda's core, halo, and spiral arms. But perhaps its most famous achievement in this regard is the FAT survey, short for Panchromatic Hubble Andromeda Treasury, the PHAT survey, 2010 to 2014. This ambitious project used Hubble's cameras to capture a third of Andromeda's disk across 6 different wavelengths of light, from ultraviolet to near-infrared. The result? Are over 117 million stars catalogued individually. A composite mosaic covering 614 square arc-minutes, one of the largest mosaics Hubble has ever created. A detailed mapping of star clusters, gas clouds, and stellar evolution regions. A discovery of tens of thousands of variable stars, aiding our understanding of how stars live and die in a spiral galaxy environment. In fact, the FAT survey remains the sharpest and most detailed image of a galaxy ever obtained, resolving Andromeda into individual stars, something previously possible only for our own Milky Way. It's essentially a stellar census of another galaxy. Other missions and observatories. While Hubble garners much of the glory, it's far from the only mission helping us understand Andromeda. GALEX, Galaxy Evolution Explorer. This ultraviolet space telescope revealed hot, young stars and ongoing star formation in Andromeda's arms. UV light is critical for detecting newly formed stars that are otherwise hidden in visible light images. Chandra X-ray Observatory. Chandra studied Andromeda's central region in the X-ray spectrum, revealing high-energy phenomena, such as neutron stars, supernova remnants, and the activity surrounding its central supermassive black hole. Spitzer Space Telescope. Spitzer, now retired, observed Andromeda in the infrared, detecting cooler dust and gas regions where stars are born. It helped identify massive molecular clouds hiding within the spiral arms. JWST, James Webb Space Telescope. Although JWST's primary mission is focused on the early universe, it will almost certainly contribute to the study of Andromeda in ways never possible before, especially in the mid-infrared, allowing astronomers to examine older stellar populations and dust-shrouded regions in Andromeda with exquisite sensitivity. Ground-based telescopes. Massive Earth-based observatories such as the Keck Observatory in Hawaii, Subaru Telescope, VLT, Very Large Telescope, in Chile, and others use adaptive optics and spectroscopy to analyze Andromeda's stars, rotation, and halo structure. Spectroscopy, in particular, helps identify chemical compositions of stars, revealing their ages and origins. What amateur astronomers can see and do. Even though professionals have the most powerful tools, amateur astronomers can absolutely observe and photograph Andromeda, and many do, with stunning results. Finding Andromeda. The Andromeda Galaxy lies within the Andromeda constellation, which is part of a larger family of constellations that include Pegasus, Cassiopeia, and Perseus. Here's how you can find it. A look toward the northeastern sky in autumn if you're in the northern hemisphere. Use the Great Square of Pegasus as a starting point. From the star Alpheratz, move up and slightly to the right. The galaxy lies near the star Merope. Under very dark skies, M31 will appear as a faint, elongated smudge to the naked eye. Using binoculars and telescopes. With binoculars, 7 by 50 or 10 by 50, Andromeda appears as a soft, oval glow, an ethereal shape stretching several degrees across the sky. You'll begin to see the core and part of the halo. With a small telescope, 4" to 6 aperture, more structure emerges, particularly the brighter core and surrounding fuzz of the disk. In dark skies, you might detect M32 or M110. With larger amateur scopes, astrophotographers can capture the dust lanes, star-forming regions, and even color gradients in Andromeda's spiral arms. Astrophotography. Using long-exposure photography, amateurs are now capable of capturing images that rival what professionals achieved just decades ago. Modern CMOS and CCD cameras paired with tracking mounts allow for multi-hour exposures, revealing deep structures, spiral arms, dust lanes, satellite galaxies, and even the hints of interaction with M32 and M110. Many amateur astrophotographers contribute their images to citizen science programs, help identify novae, or even discover transient phenomena in Andromeda. Andromeda from different locations. Andromeda is a northern sky object, best seen from locations above the equator. The further north you go, the higher it appears in the sky. In the northern hemisphere, the best months are September through November. During this time, Andromeda is high above the horizon in the evening. In the southern hemisphere, Andromeda appears much closer to the northern horizon and is harder to observe. You'll need a very clear, dark northern horizon and optimal conditions. Light pollution is the biggest enemy here. Even though Andromeda is the most distant object visible to the naked eye, it disappears easily in urban or suburban skies. A trip to a dark sky park or a rural area can make all the difference. Why observing Andromeda matters. Every photon that reaches us from Andromeda is 2.5 million years old. That light left the galaxy long before Homo sapiens even existed. To gaze at Andromeda is to look back in time, to witness a galaxy as it was when our ancestors were still primitive mammals. Through both scientific observation and simple visual wonder, Andromeda connects us to the universe in a profoundly humbling way. It teaches us how galaxies form, evolve, interact, and even die. But it also shows us that, in a cosmos of unimaginable size, we are not isolated. We are part of a community of galaxies, with Andromeda being our closest relative and eventual cosmic partner. And the best part? You don't need a degree or $1 million observatory to appreciate it. All you need is a clear night, a little patience, and a pair of eyes willing to wonder. When it comes to understanding the universe, there's no better natural laboratory than the Andromeda Galaxy. Its sheer proximity, complexity, and similarity to our own Milky Way make it a cornerstone of modern astrophysics. In fact, it's not an overstatement to say that what we know about galaxies at large is deeply shaped by what we've learned, and continue to learn, from Andromeda. This segment explores the scientific importance of Andromeda, not just as a beautiful spectacle in the sky, but as a foundational object in our quest to comprehend the cosmos. Whether it's the birth and death of stars, the behavior of dark matter, or the dynamics of galaxy collisions, Andromeda is where theory meets observable reality. A nearby template for galaxy formation and evolution. Galaxies are the building blocks of the universe, but for much of human history, we couldn't even confirm their existence outside the Milky Way. That all changed when Edwin Hubble studied Andromeda and revealed it as a separate galaxy, a revelation that opened the doors to understanding galaxy formation and evolution. Andromeda, or M31, is especially crucial because it represents a mature, spiral galaxy with many features similar to the Milky Way. This means that scientists can observe its components in detail, then apply what they learn to broader galactic models. Why Andromeda is ideal. Close enough to resolve individual stars. A similar structure to the Milky Way, barred spiral. A similar age and evolutionary state. Active star formation in its spiral arms. Past interactions and mergers evident in its halo and outer disk. Through Andromeda, we can study galactic dynamics, star formation cycles, chemical enrichment, and even black hole behavior in a galaxy that mirrors our own in many key ways. Testing models of stellar populations and star formation. One of the fundamental challenges in astronomy is understanding how stars are born, evolve, and die, not just in isolation, but as part of the galactic ecosystem. Thanks to high-resolution imaging from Hubble and other observatories, astronomers have catalogued millions of individual stars in Andromeda. By analyzing their luminosities, colors, spectra, and distribution, scientists can build stellar population models. This allows us to date different regions of the galaxy, understand the initial mass function, how many small versus large stars form, track metallicity gradients, abundance of elements heavier than hydrogen and helium, identify starburst events or quenching periods in Andromeda's past. Moreover, researchers have discovered several generations of stars, particularly in the bulge and halo, showing that Andromeda, like the Milky Way, experienced waves of star formation possibly triggered by interactions or mergers. Understanding galactic halos and satellite galaxies. Galactic halos are vast, dimly lit regions filled with old stars, globular clusters, and most intriguingly, dark matter. Studying Andromeda's halo provides crucial clues to how galaxies accumulate mass, grow over time, and absorb smaller companions. Thanks to deep imaging surveys and spectroscopic data, astronomers have identified tidal streams, ribbons of stars stripped from smaller galaxies consumed by Andromeda. Globular clusters, ancient, tightly bound star groups offering insight into early star formation. Extended stellar populations, evidence of multiple past mergers. The halo of Andromeda is an archaeological site of cosmic proportions. Each star and stream within it is a record of a galactic merger, collision, or accretion event that shaped Andromeda's structure, illuminating the nature of dark matter. Perhaps one of the most significant contributions Andromeda makes to science is in the study of dark matter. Despite being invisible, dark matter accounts for roughly 85% of all matter in the universe, and its presence is inferred by how it gravitationally influences visible objects. Rotation curves and the dark matter halo. One of the strongest indicators of dark matter comes from galactic rotation curves. According to Newtonian physics, stars further from the center of a galaxy should orbit more slowly. However, in both Andromeda and the Milky Way, outer stars move at nearly constant speeds, suggesting that there's much more mass present than what we can see. This discrepancy is attributed to a dark matter halo, a vast, invisible sphere surrounding the galaxy. By measuring orbital velocities of stars and gas at different radii, astronomers can model the distribution of dark matter in Andromeda. Andromeda's mass, including its dark matter component, is estimated to be about 1.5 trillion solar masses, though this number is still debated and refined with each new study. Simulating cosmic collisions and galaxy mergers. Andromeda isn't just a tool for studying galaxies in isolation. It's also a key test subject for understanding galaxy collisions, especially in preparation for the Milky Way-Andromeda merger predicted in 4.5 billion years. Through simulations and detailed star mapping, scientists have identified signs of past mergers, such as asymmetric arms, ripples in the disk, and orphan star clusters. The influence of satellite galaxies like M32 and M110, which have likely disrupted Andromeda's outer structure. Patterns in stellar orbits that hint at ancient gravitational encounters. Simulations based on Andromeda's structure and motion have helped refine models for how galaxies coalesce into larger structures, how elliptical galaxies form, and how star formation behaves during such massive events. The role of supermassive black holes. At the center of Andromeda lies a supermassive black hole roughly 140 million times the mass of the Sun. While not as active as those found in quasars or radio galaxies, it still plays a critical role in shaping the dynamics of the galactic core. By studying the motion of stars near the black hole, astronomers can confirm massive central objects predicted by galaxy formation models. Study low-level accretion activity and compare it to the Milky Way's Sagittarius A star. Understand how black holes interact with surrounding stars and gas without dominating their environment. Andromeda thus serves as a benchmark for understanding low-luminosity active galactic nuclei, AGN, and the relationship between galaxies and their central black holes. Cosmic distance ladder and extragalactic calibration. Determining distances in the universe relies on a cosmic distance ladder of increasingly indirect methods. Andromeda plays a key role in this chain. Because it's so close and well studied, astronomers have used Cepheid variable stars, which have a known brightness-period relationship. Are our Lyrae stars, which also serve as standard candles. Are eclipsing binary systems, allowing geometric distance calculations. Each of these methods has been used in Andromeda to fine-tune the Hubble constant, a measure of the universe's expansion rate. By calibrating our distance to Andromeda with high precision, we improve all extragalactic distance measurements, leading to better models of the universe's size, age, and growth. Testing galaxy formation theories. Finally, Andromeda is a critical touchstone for CDM, lambda cold dark matter, cosmology, the prevailing model of how the universe formed and evolved. According to this model, galaxies form via the gravitational collapse of dark matter over densities, the cooling and condensation of baryonic, normal, matter into stars and gas disks, mergers and hierarchical growth over cosmic time. Andromeda's structure, satellite systems, star formation history, and dark matter halo all align remarkably well with these predictions. However, discrepancies, such as unexpected features in its outer halo, also challenge and refine existing models. That's what makes Andromeda so vital. It's close enough to test fine details, large enough to be a typical major galaxy, and dynamic enough to challenge our assumptions. A cosmic mirror. In many ways, studying Andromeda is like looking in a mirror that reflects not just our galaxy, but our place in the cosmos. It offers a glimpse into the past, a window into universal processes, and a preview of the Milky Way's own fate. As we continue to unlock its secrets, Andromeda will remain one of the most important and illuminating objects in all of astronomy, a cornerstone of science, wonder, and exploration. In the grand finale of our journey through the cosmos, we turn our gaze not just outward toward the Andromeda Galaxy, but inward, toward what that galaxy means to us. Because for all the science, data, and discoveries we've explored, there's something deeply human at the heart of it all, a search for understanding, for connection, and for perspective. Let's take a moment to step back, not just from the telescopes and simulations, but from the very Earth beneath our feet, and reflect on our place in the universe, and what Andromeda teaches us about it. Close, yet incomprehensibly distant. On a cosmic scale, Andromeda is incredibly close. At roughly 2.5 million light-years away, it's a mere skip across the vast ocean of space. Light from Andromeda takes 2.5 million years to reach us, and yet, it's the closest spiral galaxy to our own. It's so close, in fact, that the gravitational dance between it and the Milky Way is already underway. But despite this closeness, the distance is so enormous it defies true comprehension. If you could travel at the speed of light, the fastest possible speed in the universe, it would still take you millions of years to get there. Even our fastest spacecraft would take billions of years to reach its stars. That paradox, that something can be so near and yet so impossibly far, is a reminder of the immense scale of the universe. And yet, from the comfort of our backyards, we can raise our eyes to a clear night sky, spot a faint glowing smudge, and say, there. That's another galaxy. A whole other island of stars. And we can see it with nothing but our own eyes. That's the magic of Andromeda. We are not alone. Andromeda humbles us. It reminds us that our Milky Way is not unique, nor alone. For centuries, we thought our galaxy was the entire universe. But now we know that there are billions of galaxies, each containing billions or even trillions of stars. Andromeda is just one of them. But it's our neighbor, our counterpart, and, one day, our partner in cosmic union. Its presence changes how we view the night sky. Instead of thinking of stars as lone beacons, we now see them as parts of vast structures, swirling, interacting, growing, and merging across time. And in this grander view, we are not at the center of it all. We are part of it all. We are made of the same stardust that fuels the brilliant blue stars in Andromeda's spiral arms. The atoms in our bodies were forged in ancient stars that once lived, died, and scattered their elements across space, just like the stars in Andromeda's past. We are connected, not just in observation, but in composition. The universe didn't just give rise to us. We are a way for the universe to observe itself. A shared future. Andromeda doesn't just symbolize the vastness of space, it also embodies the passage of cosmic time. The future of our galaxy is already written in its stars. In 4.5 billion years, Andromeda and the Milky Way will collide and merge. This won't be a violent smash, but rather a graceful cosmic ballet, as gravitational forces reshape both galaxies into something new, an elliptical galaxy often nicknamed Milkomeda. This is a future that's beyond human scale, long after the Earth has changed, and perhaps long after humanity has moved on or evolved into something else. But it's a reminder that everything in the universe is in motion. Nothing stays static. Not stars. Not galaxies. Not even space itself. And yet, that collision will be a kind of reunion. A merging. A return to unity. And it will be the most significant event in the local group of galaxies, a reshaping of the night sky for whatever civilizations may remain to watch it unfold. A galaxy worthy of wonder. What is Andromeda, really? It's a galaxy of roughly 1 trillion stars. A swirling collection of light, dust, gas, and dark matter spanning over 220,000 light-years. It's home to nebulae birthing stars, to ancient red giants, to star clusters and satellite galaxies, and to a supermassive black hole at its heart. But it's also more than that. It's a symbol of how far we've come, from early skywatchers seeing it as a faint blur, to Arab astronomers giving it its first written record, to Edwin Hubble revealing its true nature, and to us today, mapping it in wavelengths far beyond the visible. It's a reminder of how small we are, and how vast our potential is. Because the very fact that we can see it, study it, and understand it, is a miracle of consciousness. A testament to curiosity. A product of generations of wonder. In every stargazer's heart, there is a yearning to understand what's out there. Andromeda answers us. It says, "You are not alone. The universe is vast, ancient, and full of beauty. And this is only the beginning." A final look toward the night sky. So the next time you find yourself under a clear sky, maybe on a cool autumn night, look up. Use an app if you have to. Scan the stars. And if you're lucky, you'll find that faint, glowing patch just above the horizon. That's Andromeda. And you'll be looking, with your naked eye, at a galaxy 2.5 million light-years away. Light that left before humans existed is just now reaching your eyes. And when you see it, don't just think of numbers or facts or statistics. Think of the journey we've taken together. Think of the story it tells. Think of the billions of stars, the countless planets, the mysteries still waiting to be discovered. Think of how, in all the cosmos, we are just beginning to understand our place. And in the dark, infinite expanse of the universe, there shines our majestic neighbor, the Andromeda Galaxy. A light in the darkness. A beacon of science, of history, of myth, and of wonder. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.